determine the concentration of ions in the solution. And then some of the interpretation of the data about like the common energy storage devices. We talk about supercapacitors and batteries, how we can interpret the data, and also look at the performance metrics and what are the common mistakes that are committed by the researchers, and then I am going to highlight those common mistakes. And finally, again I will connect it to the building the sustainable society and how electrochemistry can contribute in a wide way to bring the sustainable society. So to start with, let us ask a question: what is electrochemistry, right? As the name suggests, it actually deals with the interrelations of electrical and chemical effects, right? If I just want to elaborate, it is going to talk about, right, reversibility between two effects. One is chemical and another one is electrical, right? So for instance, if you take chemical changes you want to cause by passing the electric current, this is very widely known electrolysis process, like how people produce aluminum, chlorine, it is based on the electrolysis process. So you pass the electric current and make the chemicals out of it. Vice versa also true, that you can have chemical reactions that would give rise to the electrical output. So why are we interested in electrical output? Because electrical energy is a high grade form of energy, unlike the heat energy. So once you have electrical energy, that can be converted into other forms of energy like light, heat and mechanical energy. And efficiency wise, electrical energy is going to provide higher efficiencies compared to the heat energies or thermal based systems. So this is where that we need to understand the interrelation between electrical and chemical changes that are going to happen. Fundamentally, that researchers are always interested in looking at electrochemical aspects based on three primary reasons. The first thing is, one would like to know the thermodynamics of a chemical reaction. Sometimes the thermodynamic information may not be obtained directly. One can use electrochemical data to extract thermodynamic information about a chemical reaction. The second thing about the studying the radical anions, which are like highly unstable intermediates that you produce out of the process, you want to understand the nature of such species present in the solution. We can always use electrochemical techniques to create such kind of species. And most importantly, when you want to check the quality of water, drinking water, what are the trace amounts of metal ions present in the drinking water, like lead and toxic metals that are present, whether they are present in the parts per billion range, parts per trillion range. This is where electrochemical techniques are even more powerful compared to spectroscopic or chromatography based methods. So, and for all these things, what everyone has to do is to have an idea about electrode-electrolyte interfaces, understand the electrical properties of electrode-electrolyte interfaces. This is a key in order to realize various aspects of the implications of the electrochemical studies. So just to give you a flavor of electrochemistry, it encompasses of variety of phenomena that we see day to day life. If you take a look at biologists, they use a phenomena called electrophoresis. This is a phenomena by which colloidal particles can be moved in the liquid medium by means of applying electric field. This is actually fundamentals linked to the electrochemistry principles. And the second phenomena, we always see corrosion. It's an irreversible interfacial reaction of a metal with the environment that is going to happen, and we see typically iron that is present in all these concrete buildings and also the bridges that undergoes corrosion naturally. This is very natural phenomena and electrochemical in nature, right? So then once things get corroded, that it is going to lose its mechanical properties, losing its strength, and many industries they are using these pipelines. If they get corroded, and then of course that leakage of the gas, the porous structure that develops, and we have to find a ways. Once you understand the phenomena of corrosion, we can design the things how to prevent the corrosion, right? It's a basic electrochemical reaction. At one site you have an oxidation reaction, and the other side you have a reduction reaction. If you are able to stop these oxidation reduction reactions, you can prevent the corrosion. There are various strategies that people have developed. When it comes to the technologies that already, you think about the technologies, that plating technology has been well established, electroplating of metals. So the people think about making Oscar awards, Academy Awards. It's exactly the based on principle of Faraday's first law, that how much amount of gold you want to deposit, right? So it's all governed by the quantity of electricity that you pass. And then sometime you want to prevent the corrosion phenomena, people also use electroplating. This is called galvanization. So people always use zinc as a sacrificial anode to prevent the corrosion of iron. And then the most important thing is producing commodity chemicals. Like take a look at the chloralkali process. Here electrolyte is simple brine solution, sodium chloride solution. Just do electrolysis. At the anode oxidation happens, you produce chlorine gas. At the cathode you are going to produce hydrogen and caustic soda, that is sodium hydroxide. So it's a very simple industrial and a kind of large scale industry that they employ this chloralkali process. And of course once you have chlorine gas, you can think of making other materials like PVC pipes, like polyvinyl chloride, which is being used in the construction material. So it's a kind of commodity chemical that can be implemented for making many other materials. And then of course you think about energy devices like supercapacitors and batteries, and all of us are having at least 2 batteries in the mobile phones and laptops, and the lithium-ion battery that actually fundamentally relates to the redox reaction that are happening, charging and discharging, that you see that how electrical energy is converted into chemical energy. Like during the discharging you are operating in the galvanic mode, while charging the battery it is operating in the electrolytic mode. So you are going to reverse the reaction. These are rechargeable batteries that we come across. And then electrochemical sensors, you talk about electrochemical sensors, right? So how much glucose is present in blood samples, so that can be analyzed. How the concentration terms can be converted into potentials, and then you can quantify how much glucose content is present in the blood. And also dissolved gases, let's say what is the CO2 that is dissolved in seawater, you can always determine using these sensors. And think about very famous right now that everyone is struggling to get the clean water. And if you look at the world, like if you have 97.5% water on the earth is salt water, so you cannot directly drink it. So how can we remove the salt ions from the seawater? This technology is called capacitive deionization technology. Of course you have distillation, reverse osmosis, they exist. In one case you need very high temperature to get the pure water, in another case you have to use membrane and apply very high pressure to get the pure water. But take a look at the capacitive deionization. You don't need temperature, you don't need high pressure, you don't need membrane. What you need is just apply a nominal potential of 1 volt, 1.5 volt at room temperature. So what it is going to do, these 2 electrodes are going to attract cations and anions accordingly, and you get the fresh water out of it. So most of the Middle Eastern countries, they are going to rely on this desalination technologies, not only for drinking purpose, irrigation purposes. You want a controlled amount of salt present which can be utilized for the cultivation purpose. One can use this capacitive deionization technologies, which is going to be much more efficient compared to the existing distillation and reverse osmosis techniques, which are like energy intensive process. And then think about electrochromic windows. Boeing 787, they don't use window blinds. What they use, electrochromic windows, where you can change the optical property of the material by applying potential. So you want to be like a transparent, you can just keep on pressing this button, you make it like transparent, you want to see through. You want it to be opaque, and accordingly the the color can be changed. It's a typically tungsten oxide materials are being used in these windows. It's a kind of aesthetic appeal that you have instead of having these window blinds. Such kind of electrochromic displays always very interesting to work on. So this is a kind of range of things that you can think about, phenomena, technologies, devices, and then all these are covered under the umbrella of electrochemistry. So basic is electrochemistry. So as I mentioned, when you talk about electrochemistry, that you always come across electrode-electrolyte interface. So as shown in this particular diagram, electrolyte typically being the liquid, we cannot have it like frozen thing. So you need a compartment to hold the electrolyte, and you have an electrode that is placed there. To understand the single isolated interface, we cannot do the measurements directly. We need another electrode in combination with this electrode 1, like where you want to study what is happening across electrode-electrolyte interface. we need a standardized electrode 2 whose potential is known. Then you will be able to understand what are the things that are happening across electrode 1, right. So, this is the fundamental limitation, but a standard definition of electrode is supposed to be an electronic conductor. So, what kind of electrodes one can use? We can use solid metals like platinum and gold, which act like a source and sink of electrons, and you can think about lot of early research, electrochemistry research is done on using liquid metals like mercury, amalgams, and carbon is also widely used like glassy carbon and graphite. There, because of their electrochemical robustness, people use as a working electrodes, and semiconductors are being also explored as electrodes in this electrochemical research. Coming to the electrolyte is nothing but an ionic conductor. You take NaCl, table salt, put it in water, because as such NaCl is not ionic conductor, solid form, but the moment you put it in water, it conducts electricity by passes of ions. That is called ionic conductor. Alternatively, you can also melt it. You use very high temperature, more than 500, sodium chloride can be in the molten form, which can start conducting ions, that is called ionic conductor. So, you can also see that variety of electrolytes, like sometimes people see eutectic mixtures, like you want to reduce the melting point of the salt, you can use sodium chloride, potassium chloride, this is the eutectic mixture one can use, and sometimes you can have polymer gel electrolytes. You take a polyethylene oxide and in this matrix you can add some salt so that it is like a polymer gel electrolyte. Recently, it was there in 1980s, 70s solid electrolytes. Like best example is sodium beta alumina, how sodium ions move through the alumina sheets, right. This was studied long back, but now based on this emergence of solid state batteries, that people would like to have solid electrolytes, how well ions can conduct between the anode and cathode. So, the lot of research is being done in exploring the solid state batteries, where solid state electrolytes play an important role. So, these are the classification. Electrode is supposed to be an electronic conductor, like electrolyte is supposed to be an ionic conductor. It can be in different forms, it can be aqueous, non-aqueous, or it can be molten form, right. It can be a solid form, so it does not matter. As long as it conducts ions, that is what we are interested in. And one thing is, we cannot study single isolated boundary. So, if simply I have electrode-electrolyte interface, very difficult to study what is happening at the interface. It must be paired with another electrode whose potential is known. It is a standardized electrode that I am coming to it, explain this. So, often time we come across either 2 electrode or 3 electrode type of configuration. So, when I say 2 electrode, of course you can say one of the electrodes that is of your interest, what we call working electrode or indicator electrode. The other electrode is going to be called counter electrode, because you have to complete the circuit. So, once you want to complete the circuit, in the case of 2 electrode, the counter electrode acts both like a counter electrode as well as a reference electrode. But it is not guaranteed that the potential of the counter electrode may not remain the same. It may vary during the measurements. While current is passed in the circuit, it is not guaranteed that the potential of the counter electrode remains constant. This is where people want, when they want to do very sensitive measurements, it is always recommended to go to 3 electrode measurements. So, when I say 3 electrode, one of the electrodes is working electrode, second one is the reference electrode, third one is the counter electrode. So, counter electrode completes the circuit, it takes care of passing the current. Now, the volt potential being maintained fixed or constant, between the working electrode and reference electrode. Because reference electrode has high impedance path, it may not conduct electricity. It may not conduct electricity because current always try to take the shortest path that is available. Now, always you see that current always flows between working electrode and counter electrode, but by having the high impedance path having in the reference electrode, it is because of its constant composition, it always maintains fixed potential or constant potential. So, that is the idea of having 3 electrode. In this way, we know precisely what is the potential being applied on the working electrode, at what potential molecular species are undergoing oxidation and reduction, we can precisely determine, right. But in reality, when you make devices like a battery and supercapacitor, it is a 2 electrode device, right. But fundamentally, we need to understand that what happens at electrode level. By performing very systematic 3 electrode measurements, then we understand what is happening, and finally we can end up making a good device. If you do not do this, then of course the device that we make, we may not be highly energetic or highly efficient. So this is where one has to understand that what kind of measurements we need to perform. This is very, very important. Of course, as I told, one of the special electrodes, yeah.
So if we provide negative or positive potential in the working electrode, making it cathode or anode, so is it the counter electrode that acts as the opposite potential electrode?
No, this one, when you go back to this 3 electrode measurement, so you are interested in sweeping the potential of working electrode from negative to positive.
Either negative or positive?
Yeah, either negative or positive. That means entire potential is being subjected to the working electrode. You want to understand whether a reduction is going to happen, you want to scan through it, right? Of course, these counter things are happening on the counter electrode, but you are not interested in it. Okay, so of course at one location oxidation is happening, some other location reduction is going to happen. At the end of the day, charge neutrality has to be maintained. Similarly, if working electrode is undergoing reduction, then here oxidation happens on the counter electrode and vice versa. But we are not interested in it. Our focus is only on what is happening on the working electrode. That in this way, with this particular setup, can counter electrode support it for many cycles by doing this oxidation reduction cycles without undergoing too many modifications, whether counter electrode is going to help us or not. So this is where you are going to look at it. So the special class of electrodes, we call it as reference electrodes. One is called primary reference electrode, that is called primary standard electrode, that is called SHE, standard hydrogen electrode. So if you look at the construction of standard hydrogen electrode, you have a platinum wire, you can see here this is a platinum wire, and at the end of the platinum wire you have a platinized platinum, that is like a little bit of high surface area platinum that you deposit. Because of this, it can absorb the gas molecules like hydrogen. And this particular setup is kept it in like acidic medium like protons, and you can see the kind of the way we convention represent. Anything is going from one phase, like platinum is a solid phase and hydrogen is a gas phase. This is a vertical column is used, and then subsequently it goes to aqueous phase, another vertical column. This is a common convention people use to represent electrode electrolyte interface. Anything phase boundary we are crossing, we are going to use the vertical line, and also state of the material and material is going to be mentioned here, and this is the representation for the standard hydrogen electrode. By convention, the potential of standard hydrogen electrode is fixed at 0 volt, but absolute value is not 0. Absolute value is something else, but most of the electrochemistry purposes, to make it simplified, standard hydrogen electrode potential is taken as 0. It is similar to whenever we want to measure the height somewhere, we always take sea level as a reference point. With respect to sea level, what is the height or altitude that we are going to measure. Similar way, in this analogy, that standard hydrogen electrode potential is taken as 0 and by an arbitrary convention, not an absolute convention. Okay, and then in the typical laboratory setup, it is not always easy to construct standard hydrogen electrode. Then we have some other types of reference electrodes, what we call as saturated column electrode. So the construction of reference electrode, when you look at it, you have a typical capillary, glass capillary kind of construction, like capillary, glass capillary. At the end of the bottom of this capillary, you have a porous frit. This porous frit helps in the passage of ions to have just only ionic current. And then depending on this, whether you want to use KCl saturated or certain concentration, you can keep it here. And then you have mercury, mercurous chloride and KCl paste that is available, and all this connected to a silver wire for the electrical connection. So similarly, you have silver chloride, where a silver wire is there, and that you have a deposit of silver chloride, and you keep lot of chloride ion concentration constant, because when you apply Nernst equation, right, so whatever is going to happen, chloride ion concentration is going to remain constant because you are having excess amount. So this way you are going to maintain the potential of the reference electrode constant. So the kind of changes that you brought in. So whenever electrochemistry, that most of the time voltammetry techniques or any other techniques, x axis is going to be potential. When you measure the potential, it is always important to reference against what is the reference electrode. So you can see that potential, are you fixing with respect to SHE, that is 0 volt. You can see iron 2 plus iron 3, iron 2 couple, that comes around plus 0.75 volt. If you want to reference with respect to AgGCl, it will come around plus 0.55 volt. If you want to reference with respect to saturated column electrode, it is 0.506. So it depends upon the reference electrode and it is also interconvertible. So it depends upon the convenience that we can always interconvert it according to the need, right. So now we understood that the electrochemical cells and the importance of reference electrodes. Now typically we come across two types of electrochemical cells. One is galvanic cell, like all of us know that galvanic cell is a spontaneous electrochemical cell in which chemical energy is converted into electrical energy. You can see here a typical example, standard high school example that we take, that a zinc rod dipped in zinc sulphate solution, copper rod dipped in a copper sulphate solution. Because these two electrolytes are different, they are kept in two different compartments. To have the electrical neutrality, to maintain the charge neutrality, we always have the U-tube bridge. Okay. This actually consisting of agar-agar gel with potassium chloride being used, because the mobility of potassium and chlorides are the same. So that is where because the size is similar, so this is where potassium chloride is typically used. So of course at anode oxidation happens, right, zinc convert into zinc 2 plus, subsequent electrons travel through the external circuit and do the electrical work, and then they reach to the other cathode compartment on the copper, where copper ions present in the solution, they get reduced to copper. So this is a kind of spontaneous reaction that is going to happen. And other type of electrochemical cell we call electrolytic cell, right. So it's also like a two electrode kind of construction. You take two electrodes, that one is anode and another is cathode. The electrolyte that I am showing here is the molten form of sodium chloride. Molten form of sodium chloride. So when you take molten form of sodium chloride, by definition anode is electrode which attracts anions. Cathode is the terminal which is going to attract cations. So some electrode has to attract anions that must be polarized to positive potential or negative potential. Which electrode is going to attract anions? Positive or negative? Positive. So that means anode is positively charged here in the case of electrolytic cell. So anode is going to attract anions. Something is attracting anions, that must be positively charged. So that's how you can remember anode is positively charged, whereas cathode is negatively charged. So that means irrespective of galvanic and electrolytic cell, oxidation always happens at anode, reduction always happens at cathode. So since it's a molten form of sodium chloride, you only have one cation and one anion. Then obviously the Cl minus comes to the anode and Cl minus will become Cl2 gas. It's an oxidation reaction. And at the cathode, Na plus ions go and then they get reduced to form sodium, right. So this is the typical process used to extract alkali and alkali earth metals. Electrolysis process has been extensively used to make all alkali and alkali earth metals. This is the process. And even the aluminum production by bauxite process, right. This is exactly the molten form of Al2O3 is taken, and then Al3 plus ions get reduced at the cathode and form aluminum. That's an industrial process. Okay, this is exactly the principle here. Okay, but instead of taking molten sodium chloride, if I take aqueous sodium chloride, do you think the same reactions are going to happen? No, because you have a competing cations and anions. The moment I introduce water, you also have protons and OH minus ions, right. So you know that sodium plus reduction potential is minus 2.71. So H plus plus electron is 0 volt. So before Na plus reduction happens, you start evolving hydrogen gas at the cathode. At the anode, again chloride become chlorine gas, and then also you have some hydrogen gas that formed, right, and then you will form NaOH. OH minus ions available and Na plus ions available, which doesn't undergo reduction. They will form NaOH. That is a chlor-alkali process. You are producing chlorine gas at one of the electrodes, and then overall you are forming Na plus plus OH minus, you are forming caustic soda. Okay, it depends on the nature of the electrolyte that you are using. If you are using molten form of sodium chloride, the products that you get are different. Okay, one side chlorine gas, another one is the sodium deposition. If you use aqueous sodium chloride, you are going to get chlorine gas on the anode, but cathode side hydrogen gas, and then NaOH production. Okay, that's called chloralkali process. So then if someone asks you to, how are you going to determine the electrode potentials, right? For example, I have given you the zinc 2 plus. I want to measure its electrode potential. How to measure it, right? So I have to take zinc rod and zinc sulfate and then pair with standard hydrogen electrode as shown here. If you maintain standard conditions, what are standard conditions? Temperature 298 Kelvin, pressure 1 bar, concentration 1 molar. Those are called standard conditions. So if we can maintain the standard conditions, and what the potential that you are going to measure under standard conditions is called standard electrode potentials. As for the IUPAC convention, in order to avoid the confusion, all these reactions are represented in terms of reduction format. Okay, you can see here Pb2 plus 2 electron giving rise to Pb. This is a reduction reaction, right? If you reverse it, what is going to happen? It's an oxidation reaction, right? So when you look at the standard electrode potential, as I told, H plus electron giving H2, which is 0, but lead, you can see here, what is this? Minus 0.13. If you reverse the reaction, what is going to happen? Only sign changes, magnitude remain the same. So, but to avoid the confusion, it's always try to write it in the reduction format, and this is how you determine the standard electrode potentials of any couple you want to. That's how the table is actually made. And then you can see here, this is what, the electrochemical series, and you can see that standard hydrogen electrode is 0, right? And which one has the lowest reduction potential, standard reduction potential? Lithium. That means it has a tendency to give away electron. Once electrons are available, the electrons can reduce some other species. So lithium is going to be a reducing agent or oxidizing agent? It's a strong reducing agent. So the bottom of the electrochemical series, you can see that lithium is the strongest reducing agent. And what about fluorine? Strongest oxidizing agent. And sometime you want to pick some couple, two dissimilar metals. What is the EMF of the cell you want to produce? That you get an idea from this particular table. So you can pick what is anode or what is the cathode that you want. That can be decided based on the electrochemical series. And for corrosion studies, that whenever you have two dissimilar metals, right, when corrosion happens, what is the EMF that is being developed, that how to prevent it, we also get an idea from this electrochemical series. So the three take home messages here, that H plus electron giving rise to H2, standard hydrogen electrode potential is 0 here, and then as per the convention, all these electrode reactions must be represented in terms of reduction format, right? Sign convention is very important. If you reverse the reaction, sign convention is going to change, but magnitude remain the same. So when you have the higher magnitude of the value here, that means that particular reaction has a high tendency to be converted compared to the low magnitude. And then you want to pick a specific pair of electrodes to be anode and cathode. That idea or guidance can be obtained from the electrochemical series. And corrosion related studies, anytime you are bringing two dissimilar metals, they are getting paired up, and what is the cell potential that is being developed, magnitude. Based on that, we can find what is the extent of corrosion that may happen and how to prevent it, right? Such kind of information can be extracted from the electrochemical series. Now comes to that, having understood the electrode potentials, now I mentioned that in chemistry we are always interested in the thermodynamics, like Gibbs free energy change of an electrochemical reaction, right? If I take this particular reaction, right, zinc 2 plus 2 electron giving rise to zinc, right? If I ask you to find out what is the delta G of this reaction, how do you find out? This particular reaction, I want to find out delta G of this reaction. How do you find out? right. So here go back to this previous schematic. I am going to construct this particular cell, right, zinc 2 plus, and then I have standard hydrogen electrode. Instead of standard hydrogen electrode, you can also have AgCl or something else, you can always have it. And from here, can I measure the potential? E cell can I measure, right, standard cell potential I can measure. If I measure standard cell potential, that you know that E cathode minus E anode. Of course, we will subtract, reference electrode potential is fixed. Then you know the exact potential of your electrode. And once you know this, you see here delta G, that is the change in the Gibbs free energy of the reaction, that is linked to delta G is nothing but, this is the maximum additional work can be done, right. As work, the definition of work, what is work in terms of electrical, this work what we are talking is electrical work, right. You have a charge that by how much amount the charge can be moved across a given potential, that is Q into V, right, that is Q into V. Once I have Q is nothing but NF, number of electron transferred, F is Faraday constant, charge carried by 1 mole of electrons is called Faraday constant. What is the number? 96,500 coulomb per mole, okay. So this much charge that is available, and if I have more potential I can do more work, right. If more charge is available but less voltage there, that I cannot do more work. So that's why it's a kind of Q into V, right. So that Q is nothing but NF, charge, how many electrons that are transferred into Faraday constant, that is charge carried by 1 mole of electrons into voltage. So when you put it here, that's what we get the expression, delta G is linked to minus NFE. Now if I know the standard cell potential and I know number of electron transferred, in this case N equals to 2, F I know, I can calculate delta G of this reaction. So when delta G is negative, we know that it is a spontaneous reaction, and similarly E cell is positive, it is a spontaneous reaction. In this case, zinc never has a tendency, zinc 2 plus never has a tendency to become zinc, because it is a negative, potential is going to be minus 0.76 volt. But if you write the reaction the other way, that zinc is going to zinc 2 plus 2 electrons, that is a natural tendency, zinc would like to get oxidized. That is a spontaneous reaction. So you can predict the spontaneity of the reaction and extent of the reaction, that you can predict based on these numbers. Okay, now comes to the Gibbs, that Nernst equation, that once you know the Gibbs free energy, that you want to measure the things under non-standard state conditions, right. So standard state is whenever represented is delta G degree. In non-standard conditions, the delta G is given by delta G naught plus 2.303 RT log Q, that is reaction quotient. Reaction quotient is nothing but concentration of the products raised to their stoichiometric coefficients to the concentration of the reactants raised to their corresponding stoichiometric coefficients. So once you substitute, in place of delta G we have minus NFE and delta G naught minus NFE naught, then we reorganize this equation. So what we are going to get, now there is a link between potential and concentration terms. There is a link between potential and concentration terms, right. So suppose if I plot, my y-axis is going to be E and x-axis is going to be that log of concentration terms I am putting as Q, reaction quotient. That Q is nothing but, this is the thing, okay, concentration of products divided by concentration of reactants. What should be the nature of the plot? So my y-axis is the potential, x-axis is log of Q. Equation form is E equals to E naught minus 2.3 RT by NF log Q. Am I going to get graph like this, which way? Negative slope, right. What is this value intercept? E naught, correct. What is the slope? 2.303 RT by NF. What is this value? If N equals to 1, that is called, that's an NS10 slope, that is 59 millivolt. For 1 electron transfer, R is a universal gas constant, T is temperature, standard condition 298 Kelvin, F is 96,500 coulomb per mole. If you substitute, this is going to be 59 millivolt, and you see that I can have, when log Q becomes 0, it is a standard potential, right? And then I can vary my potential by tuning the log Q, that is the concentration terms. That is concentration terms. This is a very important relation which is going to provide an idea about how the potentials, it can be electrode potentials or the cell potentials, can be varied as far the concentration terms are concerned. So that is why an NST equation is very, very important in understanding these aspects under non-standard conditions, right. Once I know delta G, right, thermodynamic parameter, that gives free energy, we always use, because most of our chemical reactions we perform under constant temperature and pressure, delta G is always used. Of course, we want to find out the entropy change of a reaction, delta S, that is given by negative of partial temperature derivative of delta G. So what you are going to get, delta S is NF delta E by delta T. What is delta E by delta T? This is the temperature coefficient of electrochemical cell, temperature coefficient of if I can measure, if I, let us say I have a lead acid battery and I want to measure its cell potential, right, as a function of temperature. I monitor how cell potential is going to vary as a function of temperature. If I get the data, I know N value and I know F value, I can find out delta S, that is entropy change of a cell. Once I know delta S, change in the entropy is linked to dq by T. dq by T, I can estimate how much heat get generated during charging and discharging. During charging and discharging, and I know the temperature rise, I can measure temperature by thermocouple, right. If I want to estimate, because in the battery whenever you charge and discharge, it is not like 100% efficient. There are all some way dissipation that is going to happen, heat dissipation. You might have noticed sometime when you charge your battery, some heat comes up, right. So what is the parameter that is there, that is linked to the temperature coefficient of electrochemical cell, that is dE by dt. If I can make a measurement of how cell potential varies as a function of temperature, and from there I can estimate delta S. Once I know delta S is linked to dq by T. So I measure the temperature rise, how much, and I can estimate how much heat is being dissipated. So that way you can measure it. And once I know delta S, I know delta G, obviously you can find out enthalpy change of the reaction, that is delta H. So that is the equation given here.
That logarithmic graph, that Q is there at log Q.
Yeah.
That Q somehow signifies like as the cell ages, the potential drops because the concentration also keeps.
Yeah, it's an equilibrium. That how the equilibrium, is it going in the forward direction or backward direction? But the rate at which equilibrium is going to change, that is dictated by Q. That's why it's called reaction quotient. Whether it's going in the forward direction, whether it's going in the backward direction, right? And accordingly, that cell potential varies.
So when the cell ages,
Yeah.
so it degrades because of that factor also.
Yeah, that you can correlate in that sense also. That with the cell ages, what are the active masses that are getting changed, right? That you can also link it to that. So we are always talking in terms of reversibility aspect, because an NST equation is meant for the reversibility aspect. Of course, you can also take the case of irreversibility, as you said, aging of the cell, that you can always link it how the cell potential varies, with the aging. That you can. So I can put everything in one triangle now here, that linking between the thermodynamic parameters and the electrochemical parameters, that you can see that what is the relation between standard electrode potential versus delta G, standard Gibbs energy change, that is given by minus NFE. And at equilibrium, you know that there is no current passes, that standard cell potential is going to be 0, E cell is going to be 0, that is where E naught equals to RT by NF ln K. This is a equilibrium constant. We can determine the equilibrium constant of the reaction also from these electrochemical measurements. and delta G is 0 is the equilibrium condition. Okay. So, this is the kind of relationship between electrochemistry and thermodynamics, and various parameters can be extracted. Okay. So, now we having some understanding about the basics. Now we move on to the work like the techniques or the instrumentation part. So, today evening you have some hands on that you will be using one of such equipments, right. So, you can see here we need two things. One is your electrochemical cell that shown here, and you have typically either 2 electrode or 3 electrode kind of test configuration, right, test fixture, and then it has to be connected to a instrument, what we call it as electrochemical instrument, and it is typically a potentiostat or galvanostat, right, and it is like a block box. I mean, mostly we do not know what is inside, but there are a lot of electronic circuitry is available, and the electronics are going to apply potentials in a constant manner and measure the also precisely, and sometime you want current at your wish, you want to apply current signal and measure the current in a precise way. So, all these different modules are available inside this box, okay, and we mostly control this one through the software, that from the software which technique you want to choose, what are the parameters that you want to give, and then what is that you want to measure, right, that is our task. But software guides the internal electronic circuit to provide all those what we need, okay. That is a kind of basic thing. And of course, and some of you may be having different types of equipment like Solartron Analytical, Auto Lab, and nowadays palm sized potentiostats are available, and even you can interface in your mobile phone using an app. You can do the measurements that people always use for on-site diagnostics. Anyone having testing like a diabetic thing, right. So, you can always take the blood sample and in a small thing, and then and there itself connect, and from your mobile also you can get the reading. So they are available from very big instruments to the portable size. There is a kind of range of things, and most often this is a slide I want to give to everyone, which provides you the comprehensive view of electrochemical techniques, right. So, as I told again, fundamentally we are interested in electrode electrolyte interface, and what are the interfacial techniques that we come across. They are broadly classified into two categories. One thing is static technique, that means current passing is 0, current equals to 0. That technique in which there is no current flow, what we are going to measure is potential versus time, that is called potentiometry. When there is a non-zero current, again you have two situations, you can have controlled potential, you can have controlled current. Once you do the measurements under controlled current, non-zero condition, that is called controlled current coulometry. As I told, coulometry, this is charge, coulomb, the unit of charge is coulomb, that if you measure current versus time, that is called coulometry. And once you have controlled potential, again potential can be imposed variable manner or fixed manner, okay. So, once you apply a fixed potential and measure I current, that is called amperometry, and then you measure I versus t, that how current varies with time, that is called controlled potential coulometry. And most of the time, most of our electrochemistry people always use variable potential, that means dynamically you are varying the potential and measuring the current response, right. This is where lot of these things come into picture, and whether you are going to stir the solution or you do not want to stir the solution. So, this is called stirred solution and quiescent solution, that means without stirring. So, there is a famous technique called stripping voltammetry. So, stripping voltammetry, as the name indicates, voltammetry, that means you are dynamically varying the potential and measuring the current. So, in the stripping voltammetry, you want to determine the concentration of lead ions present in the drinking water. This is the technique people use, and it is going to give the precise way of measuring the concentration up to parts per billion. And then three famous techniques that you can use: linear sweep voltammetry, LSV, and you have differential pulse voltammetry and also cyclic voltammetry, right, cyclic voltammetry. So, you can extract a lot of information by doing all these measurements. I am going to mention in my upcoming slides. So, this is a kind of broad classification of electrochemical techniques that one can use irrespective of your field that you are doing, whether it is sensors or batteries, supercapacitors or fuel cells, So these are the techniques that you are going to broadly use. So one simple example of potentiometry. Potentiometry technique is a very simple technique, but it has a wide implications, right? So if you look at this construction, okay, I am giving an example of taking a drinking water. I want to determine the presence of, let's say, copper ions present in the drinking water. I take the solution of water here, right? What I need to do is, this is my water I want to test. I need to keep 2 electrodes. What are those 2 electrodes? One is reference electrode whose potential is fixed, another one is called indicator electrode or working electrode. And then I connect it to a potentiostat. The potentiostat is going to give the reading. So once I know the potentiostat reading, that is E cell, and I know the reference electrode potential. Of course, junction potential sometimes can be ignored. They are like very, very small value in the order of 1 or 2 millivolt. You can ignore. So from here you can determine what is unknown here. Yeah, E indicator electrode is unknown. Once from this I know E indicator. Now you see that E indicator is connected to this Nernst equation, that is standard electrode potential of copper minus 0.059 by 2 into log of 1 by activity of copper 2 plus. Activity of, so what is unknown here? Activity of copper 2 plus is unknown, because this E indicator we are getting from here. By having Nernst equation, I know this value, I know everything, and I only don't know activity of copper 2 plus. Clear? If I want to determine chromium ion concentration, same thing, sample solution, I keep a reference electrode, I keep an indicator electrode, and I measure the potential. That is cell potential, and I know the reference electrode potential. So from these two I will get the what is the potential of indicator electrode. Once I know indicator electrode, how it is linked to concentration? By this equation. Because Nernst equation, you know that copper 2 plus 2 electron giving rise to copper. If I apply Nernst equation on this, E equals to E naught minus 0.059 by 2 log of activity of copper divided by copper 2 plus concentration. Because you know solid concentration we always take it as 1. That is what exactly I have written. That is what it exactly. So that is the beauty of potentiometry, right? So there is no current passing in the circuit. There is no current. Current equals to 0. Current equals to 0. What is that I am measuring? Potential. Once I measure the potential, how it is linked to concentration? This is the equation.
How chromium concentration is known? You said chromium solution, right?
I don't know. That is unknown. That is unknown. So I know the potential of indicator electrode. And then in this equation, what is unknown parameter? Concentration of chromium or copper, whatever we are taking.
Whichever solution you are taking.
That we will determine.
Typically, this could be some sensor kind of applications.
Correct.
You want to check whether it is within threshold or in safe limits, higher limits.
Exactly. So we do a calibration curve first. We do a calibration curve. So initially we will want to calibrate it. So what is the potential corresponding concentration? Then we take unknown solution and whether it is following that calibration curve or not. So in this way we are going to validate whatever measurements we are doing is correct or not. Okay. So that way we can do it, and in fact the principle of pH meter, you can take pH, it's a glass bulb which helps, having the differential proton concentration, you are able to detect sensitively, and this glass is a very special glass, right? And again it is based on the principle of potentiometry. So if you again Nernst equation, E equals to E naught minus RT log of pH. So how the potential value you are reading, and accordingly the activity of protons can be estimated. Okay. As I mentioned that you want to determine the level of CO2, because carbon dioxide always dissolves in seawater, right, forms carbonic acid, right, H2CO3. Again it decomposes and it's not stable, right. You want to find out what is the dissolved amount of CO2 present in the seawater. You can use potentiometry technique. You can see this equilibrium, CO2 plus H2 are giving rise to bicarbonate and hydronium ions. And I know that in electrochemistry I can measure the potential linked to the concentration of ions. Now gas molecules are converted into from some kind of ionic form. If I know the concentration of bicarbonate ions in the water, 1 mole of bicarbonate is produced by 1 mole of CO2. I can back calculate how much CO2 is getting dissolved in the seawater.
So hardness measurement instruments also work on the same principle.
Hardness, they have some indicators like EDTA, and they have to form a complex.
You don't have electrometric methods.
Yeah, to some extent we can do, as you told, total dissolved salts for example, TDS and some alkalinity test, those things can be done.
Hardness, TDS.
Hardness we need because Ca2 plus, you are talking about Ca2 plus and Mg2 plus, this bring the hardness to the water. We need a special complex, which will form a complex. This is called ligand. It's a multi-deltant ligand, EDTA, and from there you will find out how much Ca this precisely. Okay, yeah. And most of the time you have interference. Sometimes some other ions may interfere, right? And then how to bring the selectivity, that is most important. So based on that you have to choose the method. Okay. So similar principle applies if you want to find out amount of gases that dissolve in the blood sample. Again you can take a blood sample and again do the same thing, apply an Nernst equation. From the potentials you can estimate the concentration of ions and you can find out. So now I am switching gears because we come to this electrochemical energy storage devices, right? I broadly classified into two categories, supercapacitors and batteries. Of course fuel cells also come under electrochemical energy storage devices, but in the case of fuel cells, as long as you supply the fuel, you are producing the electricity. There is nothing concept like rechargeability in the case of fuel cell, whereas these two devices you can charge and discharge. That means one time chemical energy converted into electrical and vice versa. But in the case of fuel cell, as long as you are supplying the fuel, right, H2O2, you are producing water, that device only operates in one way, that is you are producing the electricity. But I am taking these two examples that as I mentioned, electrical energy is a high grade form of energy. That is where we want to develop devices which can store electrical charges, right? And the two such examples that I am giving here, one is capacitors, another one is the batteries. And then in electrochemistry we always come across the two terms, one is non-Faradaic and Faradaic. If you remember Faraday, you always say non-Faradaic and Faradaic. When I say non-Faradaic, that means there is no charge transfer across electrode electrolyte interface. Only charge is being held in electrostatic manner. So if I take a capacitor for example, I polarize one electrode positively and another electrode negatively, it is going to attract counter ions accordingly, and there is no charge transfer across this interface. It is going to hold and then produce the energy. So that is called the simple non-Faradaic means of storing the charge. Whereas batteries involve Faradaic way of storing the electrical energy. That means when lithium ions getting inserted into graphite, you have a chemical reaction that is happening. So that charge transfer lead to the storing of electrical energy. Similarly, when you take fuel cell, how this H2 plus O2 combine producing water, because you don't want any carbon footprint, your byproduct is going to be water, and at the same time you get electrical output. That I am not going to discuss here. Okay. So fundamentally we always have to select the materials, what kind of materials that we want to make, because if you look at ultimately what we are interested in the energy, that what is the energy that is produced by the device. Energy is again dictated by two parameters, one is the charge, second one is the voltage. So charge is defined by the capacity of that particular material, how many ions it can store per unit weight, that is called charge. And volt means what is the difference between the anode and cathode potentials, that gives the voltage. So and of course electrolyte plays also an important role, what kind of electrolyte we have to choose. So when you talk about materials, right, so typical materials that we come across, that carbon based materials, because carbon is highly versatile material in the periodic table. All of us know about graphite and diamond, these are the two allotropes of carbon, right. One is an electrical conductor, another one is electrical insulator. Diamond is the hardest material that you know of, right, but you look at the bonding Graphite and diamond, they varies only in type of bonding. One is sp2 hybridized carbon, another one is sp3 hybridized carbon. As I told, if you take any biomass or a simple coconut shell, if you take and burn it off, what you get is charcoal. And then that charcoal you can activate it by, there is some called a chemical activation and get the porosity. That's called when you have porous materials, right? We take 1 gram of material, it can occupy the surface area similar to the soccer field, area of the soccer field. So that is a advantage with the carbon. That means you can have the porous materials which can store lot of ions inside their porous structure, right? So commercial supercapacitors, they use these porous carbon materials to make the devices, but there is no charge transfer across electrode electrolyte interface. On the other extreme, if you take highly crystalline form of carbon, that is graphite, if you take, which is a very standard anode material that used in lithium ion battery. The lithium ion battery you are using in a mobile phone has graphite. It's a layered structure, and how lithium ions getting inserted, right? So this is where it stores the charge. Look at the beauty of carbon. You can tune its structure, microstructure the way you like. I use high temperature, high pressure, I make it highly crystalline. I use low temperature and other chemical process to make it highly porous, right? And these two devices are commercialized. Okay, that is the beauty of carbon. And of course, you have third category that people always use metal oxides, metal sulfides, right? The transition metal oxides, they are known to exhibit multiple oxidation states, right? Can I have redox reactions that are confined only on the surface? When I have redox reactions confined on the surface, they can be very faster compared to the bulk redox reaction that happen in the standard battery materials. So that's where you always come across, capacitive type, pseudo capacitive type, and battery like kind of characteristics.
MO is also an example of this.
Yes.
For
Yeah.
lightning production we use.
Yes.
this,
Yes. Molysulfide you are talking about.
Metal oxide varistors.
Huh. The composition is most important. Of course, you can tune the morphology.
At
The,
very high voltage only they conduct.
okay.
Otherwise they don't conduct. Usually any electronics device circuit we put that in parallel so that whenever 6 kV, 10 kV kind of lightning strike happens, so at such high voltages it gets activated and then slowly it decomposes. So it's able to take up n number of lightning strikes.
Okay.
We use in the outdoor equipments.
Okay. Yeah, it all depends on the dielectric strength of that material. So again, what I am talking about, typical transition metal oxides, right? So once we have the material that I told, the typical materials that we have, and next step is to process them in the form of electrodes. So if I want to process them in the form of electrodes, right, one of the examples that I am taking materials are carbides. These are the special class of materials, mexenes, right? So if I have materials like this, I can process them in electrodes in broadly two ways. One way is I can simply filter it and get a film like this, what we call it as freestanding film. So that means I have a solvent or water like this, and material is dispersed in this medium, and then I simply filter it over the filter paper, and water will go through the filter paper, and what I get is a restacked things and get the material like this. This is called freestanding electrode. Here we don't use any conductivity to our binders. In the second category, when I get this powder like this, which is a universal method of processing electrodes, so you need to bind the particles together. Then you need certain amount of binder. Again, how much amount of binder you want to use? It depends on us. If you use more amount of binder, it is going to block lot of sites. So let's be as minimal as possible. And even can you use 1% binder? It may not give the good mechanical integrity. So we need to be somewhere in between. And it's again, I just give in my research, sometime I want to make 95-8% is my material and 5-8% is my binder. So in this case, because metal is highly conducting, I don't need to add any conductivity. So this way I can form the electrodes. So and then this is a typical Swagelak setup. As you can see here, it's a T-shaped Swagelak cell. It has 3 electrodes: working electrode, counter electrode, and reference electrode. So when you take working electrode, here this material is a working electrode, and I am taking counter electrode as carbon material because carbon is highly electrochemically stable. Sometimes people use platinum and other metals, but when you use platinum it may form a passive film which may obstruct your measurements over the cycles. And you can have a reference electrode which are commercially available, right? As I mentioned in my initial slides, you need all this good setup, and Swagelok cell is always preferred because of various reasons compared to bath cell, because when you use a bath cell, your distance between the electrodes you cannot control, right? So for example, if I am using this kind of bath cell, it is also 3 electrode cell. I have a container and I keep these 3 electrodes. Look at the distance between the working electrode and counter electrode and reference electrode, typically more than millimeters. Whereas here, when I have this, it is a highly compact configuration, and the distance between working electrode and counter electrode is going to be less than 100 microns, less than 0.1 millimeter. But in this configuration, it is more than 1 millimeter. So an order of magnitude higher distance between the counter electrode and working electrode. Because of this higher distance, all of you know simple Ohm's law, V equals to IR. As resistance is more, it is going to drop the voltage that much, right? So if you want to do very sensitive and accurate measurements, always use the Swagelok rather than the 3 electrode configuration, because the distance between the electrodes is so large and you are going to use plenty of electrolyte here. See here, your electrolyte volume is so much compared to the area of the electrodes that you are using. It may lead to so many parasitic reactions. But in this case, if you see here, you are going to use a very controlled amount of like 0.1 ml or 0.2 ml controlled amount of electrolyte. In this way you can avoid parasitic reactions. Okay, by having this very opt test configuration, right, you are going to avoid unnecessary parasitic reactions, you are going to avoid unnecessary polarization losses, ohmic losses. That is where you have to use Swagelok configuration over the thing. As I mentioned, that again you can see that this is the graph that I am showing now, that we always use cyclic voltammetry and galvanostatic charge discharge to understand what type of charge storage is happening. When you look at here, y axis is the current, x axis is the potential. What is the shape of this CV? It is a rectangular box, right? And then as you can see here, carbon materials, they show rectangular CV, and the moment manganese oxide, ruthenium oxide you go, it also shows somewhat rectangular, right? But when you calculate the capacitance is an order of magnitude higher compared to carbon, right? So how to understand this? Appearance wise, both are following non-Faradaic way of storing the charge, but actual capacity what you get, right, 10 times more than the carbon materials. When you look at galvanostatic charge discharge profiles, you look at their linear, potential versus time is linearly varying. You may come up with some kind of situation like this, some category of materials, they exhibit broad redox peaks, right, like this, and when you look at the charge discharge profile, you see it's called sloping profile. It's called, this is a linear profile, this is sloping profile. And the third category, you see that you have oxidation peak and reduction peak, they are widely separated. Similarly here you see distinct oxidation peak and reduction peak. And when you look at the charge discharge profiles, you see a flat plateau, it is called plateau, it is called plateau. So whenever you do your research, you will get one of these 9 plots, it cannot be beyond this. Then we need to understand what type of charge storage mechanism is operating by looking at the shape of the CV curves, charge discharge profiles. Either you can have linear charge discharge profile, sloping type, plateau type. You have rectangular box, you have a very broad redox peaks on top of this capacitive envelope, and you have a distinct oxidation reduction peaks, right. It is very, very important not to report capacitance for when you look at the CVs of this kind of category, because all of you know Q is proportional to V, right, charge is proportional to V, that is Q equals to C into V. What is C here? It is a proportionality constant, it is called capacitance, right. When I take one of these plots, potential versus time, if I multiply my x-axis with the current, because this particular curve I obtained by applying a constant current. If I multiply time with the current, what I am going to get? Charge. My Q is proportional to V in this case. Same thing if I do, is Q proportional to V? Is it proportional to V? It's a non-linear. It's not proportional to V. Here, only in this case you see that Q is proportional to V. Only in the top panel, when you see such kind of profile, then only you are supposed to calculate capacitance, but you should not calculate capacitance for this and this. Okay, this is completely wrong. Do you understand? I take this plot, I multiply time with the corresponding current that I applied to get this curve, correct? So once I have current into time, that is charge. When you look at the Q versus V, it's a linear variation. Then the proportionality constant or slope, what it gives you is the capacitance. But when you take here, it's a non-linear wave, it's also non-linear. So we should not calculate capacitance in such cases. Okay, I am going to show you that example. Of course, just to remember, they are categorized into capacitive, pseudo-capacitive and Faraday type of behavior. And of course, whenever you do record, today the demo they are going to show the first in the instrument software what you are going to get current versus potential. This is a typical cyclic voltammogram that you record at a given scan rate. Once you have it, and then subsequently we want to normalize with respect to the weight or volume of the electrodes. So you can normalize with respect to gram, that is ampere per gram. You can always do that. And then further you can also normalize with respect to the scan rate that you have used. Then this y-axis unit is going to convert into specific capacitance. Look at the x-axis. What is x-axis? Potential. I reference it against AgCl. Okay, so that is very important to do it this way, and then you have to convert appropriately. Okay, I am giving an example. What do you understand from this graph? I am giving you a hint. My electrode material is titanium carbide mixine. I have three different types of electrolytes. One electrolyte is sulfuric acid, another one is lithium, another one is sodium. So now you know, based on the shape of the CVs, like what you understand when you have a rectangular CV? It's a capacitive type electrical double layer formation. When you have this kind of thing, it's a broad redox peaks, it's a pseudo capacitive type, right? So broad redox peaks, pseudo capacitive type. But you look at, I calculate capacitance here. I told you not to calculate capacitance, but I calculated. How did I calculate? Right? So you should use integrated formula. So area under the curve, you should use, again this particular capacitance I calculated to make it a fair comparison with the other types of electrolytes. But in reality, universally you have to calculate only charge, capacity, but not the capacitance. You can always do calculate capacitance, only thing for comparison purpose, not to claim the highly estimated numbers, overestimated numbers. Okay, this is very important that you follow this. Okay, and similarly when you look at galvanostatic charge discharge profiles, you can see that what you have seen in the CVs, charge discharge, you can see that sloping profiles at different current densities you record, and then you have a linear profiles that you record, right? So there should be a correlation between cyclic voltammetry and galvanostatic charge discharge profiles. So what we are going to calculate is the average capacitance. Area under the curve, so instead of using linear formula, simply how do you get the slope? If I don't have a line which is linearly varying, I cannot find the slope. If something is varying like this, I cannot estimate the slope. In this case, what I am going to take, this area under the curve I am going to take and calculate the charge and give the average voltage to estimate the capacitance. Okay, I am now moving on to battery electrodes. So of course, when you convert, when you process the electrodes, in the case of battery electrodes, you have to coat very thick materials, like in the order of 10 microns or 20 microns. So this is, people call it as, current collector. current collector. So for example, if you take lithium ion battery, people use copper as a current collector, anode material for anode material, and aluminum as a current collector for the cathode material. So on this cathode current collector, you are going to coat thick material, right? So it's in the order of 10 microns to 100 microns. So and here is electrolyte. Here is the electrolyte. Now whatever redox reaction happens within the electrode, the charge has to transfer in the C direction. So for this, we need to introduce a conductive additive. When you use a conductive additive, it is going to form a nanofilaments like this. Some kind of pathways it is going to produce. So people use acetylene block or carbon block, which can be like a nano wire. It's like a nano wire. Across the thickness of the electrode, it can transport the charge effectively. Right? This is where you can see here, if you take active metal 80 weight percent and 10 weight percent is going to be your conductive block. So this particular material is going to help in transporting the charge from top to bottom to the current collector. And of course I need a binder to keep the mechanical integrity, otherwise material will peel off, electrode may not be stable. We also have to keep the mechanical stability of the material. So this is the kind of thing, and you have to dry the electrodes properly, and then you can assemble the cells. And I think all of you know, when current versus potential is rectangular, it's a capacitive type, and what is the charge discharge profile? It's a triangular or linear form, right? And then what happens now? What is this kind of nature? You have a distinct oxidation peak and reduction peak. These are typically battery type of characteristics, and in the charge discharge also you see that clear plateau. Charging and discharging, you see the clear plateau. So in this case, what you have to do is you have to calculate the charge. You have to calculate Q. Q is nothing but current into time, right? And then battery community, they are always interested to report in terms of ampere hour rather than coulombs. You know, 1 coulomb equals to 1 ampere second. So they are interested, and accordingly the conversion factor will come, and this way again you have to do appropriate unit conversion to report the capacity in terms of milliampere hour. Coulombs is a right unit, but 1 coulomb is 1 ampere second. But it's always, they always use, it's a common practice in industry way to represent in terms of ampere hour, milliampere hour. So you just convert the unit accordingly. So of course you will see that same CV profile you see here, and again normalized with respect to the weight of the electrode, and similarly charge discharge profile you see, and then you look at the x-axis here, time. Now next, if I multiply this time with the current that I used to get this plot, what I am going to get? Charge. So that is what capacity I am going to get, that is represented in milliampere hour per gram. So this is how I have to represent. And then of course when you do the same test at different current densities, let us say 25 milliampere, like 50, 100, so I am going to generate, this is called rate performance plot. When I go from low current density to high current density, how much capacity is going to vary, and come back to again low current density, how much it is going to retain. That is what is called rate performance test. And then people also report cycling stability. That means if I apply one current density, charge, discharge, and with respect to first cycle, how much I am losing after 500 cycles? Almost 10% of the capacity is lost. And then parallelly I am also going to report coulombic efficiency. So coulombic efficiency is very important parameter which talks about the reversibility of the system. When I charge and discharge, is it like how well, reversible reactions are going to happen. If there are any parasitic reactions that are happening, right, you will not be able to get coulombic efficiency close to 100%. This way you will know that there could be a problem with the purity of electrolyte, purity of the salt, or the way you make the electrodes, it has not been properly assembled. So you can estimate what's happening here. Okay, in next 10 minutes, how much time I have? Okay, I have more time. So yeah, this is the paper that I want to go through. Any questions anyone would like to ask? Yeah.
For a supercapacitor, are you electrode system is best or three electrode system? Testing supercapacitor.
If you are testing as an electrode material, 3 electrode is always good. 3 electrode. Having done all the 3 electrode measurements, then you can go, once you optimize everything, then you can make a 2 electrode device as a device to report the energy and power performance.
In case of testing, three electrode.
Anything like even battery material also doesn't matter, any energy storage material. First I have a material, I want to know what kind of capacity it can store, what is the potential window it can work, all those things I want to determine. It is always recommended to do 3 electrode measurement. Once you understand all these things, you can go to 2 electrode measurements. Okay, so this is a, yeah.
You mentioned like for lithium ion battery, it's a non-aqueous electrolyte.
Correct.
Means it's a vacuum kind of thing. There is no.
Without water, see typically water has the stability window, thermodynamic stability window 1.23 volt. So when you take water, either you can have hydrogen evolution or oxygen evolution if you go beyond 1.23 volt. So what people do is, instead of dissolving salt in water, if you dissolve salt in some solvent like carbonate solvent like EC, ethylene carbonate. So this solvent HOMO-LUMO gap, there is something called highest occupied molecular orbital and lowest unoccupied molecular orbital. This gap is more, like 3 to 4 volt. Then your voltage window is going to be more. That energy equals to Q into V. In you take aqueous electrolyte, V is limited. V is only 1.23 maximum. This is thermodynamic decomposition potential of water. If you want to make high voltage, don't use water, because you know that water when you use, you split the water to produce hydrogen gas and oxygen gas, right? But if you switch to solvent medium, then you get wider window, 3 volt, 3.6, like this you will get. Then V is increasing, right? That's what energy density means. So one, that you have to make new materials which can give higher capacity, that is Q, and you can also develop new electrolyte formulations which can give you the high voltage. So you can also think about ionic liquid electrolytes where they have even 6 volt window. But even though theoretically it gives, but at the end of the day, as a device, how much it is giving, one has to see. Okay, this is where the electrolytes going from aqueous to organic to ionic liquid. So this is the kind of trend that's going on. So this is the paper, yeah. See, if you want to know the electrochemical active surface area, there are, the people always take a flat surface like platinum, right? What they are going to measure is current, like CVs at different scan rates. When you have a flat surface, which is ion impermeable surface, okay? So if I take a platinum surface, and whatever the charges that are going to get accumulated on this surface. So what we call it as interfacial capacitance, this is in the range of 10 to 40 microfarad per centimeter square. Why this is the range that I am giving? Because the way you prepare the surface, it may not be flat. Sometimes you take platinum, the way you polish it, it may have some roughness factor in it. So because of the roughness, if it is more rough, you will get 40. If it is highly smooth surface, highly crystalline and very flat, you will get interfacial capacitance in the order of 10. Most of the time, the materials that we take, either porous or layered materials, these are called ion permeable electrodes. This is ion impermeable electrode. That means ions cannot get into the material, will not get into the lattice. They only go and stop at that surface, right? So once you have this kind of situation that you made, let's say some oxide, nickel oxide or copper, anything you make, then you do this interfacial capacitance calculation with respect to this, how much you are getting, and accordingly these many ions, these many sites that are available to be accessed by the ions. This is your reference point. So accordingly you can calculate. Of course people use BET measurements, but BET is altogether a different measurements. When you look at the thermodynamic conditions of BET measurements, you use low temperature and you use gas molecules. And the surface area what you get, it is not truly reflected in the electrochemical measurements. In the electrochemistry, we are using room temperature typically, and we are using the liquid medium, right? And there are no gaseous species. it may be a relative comparison. If I make 5 samples, I have the trend of BET measurements, surface area, and I can also have trend of electrochemical measurements. You can always do relative comparison, but absolute, it is very difficult to correlate. Okay, I think this is the way I am giving you the idea. So this is the way you can estimate electrochemical active surface area. You have to take a flat surface and see what is the interfacial capacitance. I am giving you the range, but again your surface, how it is prepared, you should know this value. Okay, if suppose it is coming in millifarad, even you take anything, it will not make much difference. If your material is giving in millifarad, it is already 1000 times more, it really does not matter which value you take here. But if it is slightly varying, then you should be careful. Okay, so I just quickly go through some of the tips. Yeah.
सर जैसे कोई बैटरी मटेरियल है क्या वो अच्छा सेंसिंग मटेरियल भी हो सकता है इलेक्ट्रोकेमिकल सेंसिंग का यूज करना चाहे
Battery materials.
बैटरी जैसे इनोट मटेरियल्स है उसको अगर मैं इलेक्ट्रोकेमिकल सेंसिंग
See, we cannot say simply like this, but you should understand in the sensing what is that you are looking for. When you think about sensing, right, what are the characteristics of the metal that metal should have for the sensing purpose? Are you looking for a conducting material or insulating material? What is that you are looking for? Right? One example I give you, if you take a pH meter, the kind of material, that active metal for sensing the protons is the glass membrane. All of you know glass is highly insulator, but it's become an important membrane material for measuring the pH. It can measure precisely what are the proton concentration. At that point of time, what is the interfacial potential difference that is being developed, that is important. In place of glass, if I say that I want to use the stainless steel, you cannot do it. So there is a specificity associated with. Again, exactly I should know what is the application that you are looking for. Okay, are you looking for the chemical robustness and different media that you want? Carbon materials are good, but again how selective they are, again do you want to functionalize them, you have to work on these things. Okay, as such we cannot tell that this material is good, otherwise we will not have this many materials. So people are doing a lot of modifications within the existing materials also, and try to find what are the issues and then modify the materials. We will discuss during the tea break, and I will specifically tell you the answer. So I suggest to go through this paper. It's a very important paper about the best practices in energy storage data reporting. So what are the common mistakes that researchers they do? I am going to discuss with the case examples. The first common mistake that researchers always do is the confusion between the capacitance and capacity. Right? I already mentioned that when to calculate capacitance, when not to calculate capacitance. Right? So here I have taken the case study. So all of you know this material is LFP, lithium iron phosphate. So what is the y-axis here? Potential, right? It's going from 2 is the lower cutoff, 4 is the upper cutoff. Then I see that discharge profile, like charge and discharge profile. If I see, what is that I see? What is the nature of this profile? It's a plateau. Can I calculate capacitance for this? Why not? But I am going to calculate. Okay, I am going to make it linear. So I take 3 regimes. This is one regime between 4 and 3.5. I can take it as a linear, and next from 3.5 to 3.25 it's also considered as a linear, and then from 3 to 2 is also linear. So in the entire potential window I have the profile which is non-linear. Now I segmented into three segments, and in each segment it is going to be linear. So in the segment 1, what is the capacitance? 0 farad per gram. And what is the capacitance in segment 3? 0. What is the capacitance in the segment 2? You can calculate capacitance only in that narrow window if you want, but this is not the capacitance in the entire potential window. But what people do, they report this number 1866 farad per gram, very high number, and then they use the formula E equals to half CV square, and then V is squared. Now it is overall window they will take 2 volt, 2 square, 4. 4 into capacitance, how much you are getting? 1000 watt hour per kilogram. 1000? Is it realistic? If you want to really calculate energy density, you take only 0.2 square, because this capacitance is only in the narrow window. When you do this, you will get around 10 watt hour per kilogram. That is a realistic number. So this is a kind of, most important is the constructive progress of the field is important. Best practices are important. By overestimating or underestimating the numbers, the field will not go anywhere. The progress in the field will be halted. Okay. She said I cannot do it, but I showed you the way to do it. But again I showed you that how people take as per their convenience. When it comes to the capacitance, they take this number. When it comes to the voltage window, they take overall window, and everything is boosted up. So this should not be done. So please remember that that's where the x-axis, it is going to give you the capacity, and you can see each potential what is the capacity, how it varies. That you can see easily. Okay. So whenever only linear profile you have, you can calculate capacitance. Non-linear profile, report only capacity. And then sometime we see that people run the charge and discharge. Look at here, right? Your charge, that is called overcharging they are doing, right? There is term called Coulombic efficiency. So anything that is related to the reversibility of the system, Coulombic efficiency should be close to 100%. You look at the charge time is more, discharge time is very rapid. When you take discharge divided by charge, right? So your Coulombic efficiency is very, very poor. That means you should be able to control. I should not be going to this potential. Can I limit my potential here? I need to control my potential in such a way that where I get Coulombic efficiency 100%. It's not that the way I like, I cannot charge like whatever potential I want. There is a criteria that Coulombic efficiency must be close to 100%. Here simply you are overcharging and there are parasitic reactions that are happening. Your electrode is irreversibly undergoing degradation. On top of Coulombic efficiency, there is something called energy efficiency. When you look at the discharge profile here, charge profile here, there is a hysteresis here. If you take area under the curve of the red, area under the curve of the blue, right? If they are overlapping, energy efficiency is close to 100%. But since they are not overlapping, energy efficiency is not close to 100%. Every cycle there is a capacitive fading that happens, and this is typically the case of conversion materials, that alloying materials that typically happens, that one should be really careful to understand the importance of parameters Coulombic efficiency and energy efficiency. In today's they are going to show you how to extract these parameters. And how do you determine the potential window, right? Suppose you set up a cell, you have no idea what should be my potential window, right? So the best thing is, you don't know the literature also. The best thing is, the moment you connect to the electrochemical unit, you will get a open circuit potential. That is the middle point you take, right? And go gradually in one direction. Like apply 0.2 volt, next 0.4, 0.6. So gradually go in one direction. One point is fixed. And then after beyond 0.6, you see that current is rising abruptly. That means there could be some parasitic reactions. You stop it. That is my cutoff potential this side. Once I know the cutoff potential one side, then 0.6 you keep and then go gradually minus 0.2, minus 0.4, minus 0.6 and see until where when current rises abruptly. So that should be the stable potential cutoff for your device. And one more thing, not only CV, you can also do chronoamperometry. From chronoamperometry you can also apply current density. You can also see that current density, leakage current, right? Depending on the potential that you apply, you can see that if there is too much leakage current, right? Anything beyond 0.1 ampere per gram, that is to do with some kind of leakage current or some kind of parasitic reactions. That means you should not go beyond this potential. The chronoamperometry is also powerful thing that will tell you what is the potential cutoff that you have to do, positive and negative. Clear? So one is the capacity calculation, another one is the calculating the potential window. And the third aspect, that very powerful technique, that is electrochemical impedance spectroscopy. That whenever you do EIS measurements, unlike the CV and galvanostatic charge discharge, we are doing it an equilibrium condition, close to equilibrium condition. We apply a small sinusoidal signal and we measure imaginary impedance versus real impedance. This is called Nyquist representation. What typically expected is that you will see a kind of, sometime you don't see semicircle in the high frequency region, you will only see 45-degree line. When you have 45-degree line, that is a characteristic of porous materials. When I use activated carbon, I should not supposed to expect semicircle because there is no charge transfer resistance. I only have diffusion, that's why 45-degree line I should see. The moment I go to low frequency, I see a 90-degree line. That is related to the capacitive phenomena. And then when you see a semicircle in the high frequency and then followed by 45-degree, this is a typical of charge transfer plus diffusion, Warburg diffusion that are there. But how do I confirm this semicircle is coming because of charge transfer? Most of the time, when you have a current collector that I mentioned here and the active material, if your current collector and active materials are not ohmically coupled, you may also get semicircle. That is called interfacial impedance. Rather than the charge transfer resistance. How to confirm it? What you have to do is, you have to measure the EIS at a different potential. If it is coming from the charge transfer, by measuring the EIS at a different potential, the diameter of the circle will change. When the diameter of the circle is changing, then you can confidently say that it is because of charge transfer resistance. If diameter of the semicircle is not changing when you change the potential, right, that means it is simply because of interfacial impedance. The interfacial impedance arising between the current collector and the active material. Okay, so that lot of research articles, they use equivalent circuit models and fit the data and get all the RC parameters and explain so many things. But before that, confirm it, whether it is purely because of charge transfer resistance or interfacial impedance by performing these EIS measurements at different potentials. And semicircle is not changing here, but only that 90-degree line getting deviated. Again, that is to do with the diffusion behavior of the ions across the porous electrodes. These are very, very simple confirmations and accurate way of analysis that is very important when it comes to the measurements. And finally, this is the Ragoni chart. He was not a scientist. He was like working for the Department of Energy, United States of America. He was an economist, and many people working on supercapacitors, batteries and fuel cells, they always come up with the data, I got very high energy density, I got very high power density. But he wants to keep everything in one plot. So that's where he has this specific power versus specific energy plot, where he can make different types of devices in a single plot. You can see here supercapacitors. They are very high power devices, right? But low energy. Because in the nature of charge storage mechanism, electrostatic means you can only surface is involved, you rapid way of charging and discharging. But the only surface is being involved, amount of material is involved is very, very low, energy is less than 10 watt hour per kilogram. Whereas batteries, if you take, they are the energy devices. But the power is limited because of the sluggish diffusion of ions across the solid materials, right? So you can see this is plotted in a logarithm scale, and you look at the diagonal thing that tells about the time response. So if you just do this energy divided by power, what you get? Time. So whether it is a laboratory cell or commercial device, you can always compare the time response. But commercial devices, they take entire weight of the device, normalize. But in laboratory cells, we are only taking active masses for the estimating and normalizing the performance. So that's where time response we can always use to kind of make a fair comparison with the commercial cells. Anyway, this is my last slide. So ultimately, all of us should look into the sustainable development goals, right? And how electrochemistry is going to contribute in a large way to the sustainable development goals formulated by United Nations in the year 2015. The target year is 2030. We are very close to 4 years. that how many of these goals have been achieved. And look at goal number 7, this is affordable and clean energy. That means it's like, can we tap onto renewables, and at the same time it should be low cost. Of course, all these renewable technologies are only enabled by storage technologies because of their intermittent in nature. So we need to also develop energy storage technologies, and in fact they enable the renewables, right? And look at the clean water and sanitation. That's a problem that can be solved again based on the electrochemistry principles, and lot of CO2 that is present, right? And we see that a lot of fossil fuels we are consuming, and carbon emissions are coming, and it's a global warming effect. Nowadays, lot of research is being done, reduction of CO2, electrochemical reduction of CO2, how to convert CO2 into value added chemicals, which is freely available, right? Look at these things, and even nitrogen reduction, making some useful chemicals. So electrochemistry already played significant role in the society, societal development. Now also this is the time to use electrochemistry principles, right, to make our society clean and green manner, and this is where the electrochemistry can contribute widely to the society. In the scenario of India, right, we got independence in 1947, that can we be energy independent by 2047. This is called energy swaraj. How to achieve this energy swaraj? Look at the ongoing war situation, and now energy, right? The capacity to do the work is called energy, that our industrial society need energy, that we don't want to rely on other sources. Can we have our independence in energy, right? It is all possible through the research and development. All of us can contribute in a very small way that makes a big difference, right? So you can see that over past 300 years, how the field has evolved, how many, starting from the voltaic pile to, very compact lithium-ion batteries, right? How transformation happened. It's all like incremental progress, what people do, and passion that they have about the research, and which actually contribute, and the way we are living in the society today, right? With all our mobile phones, these are portable, not having the wall power, right? You look at the scenario and think about it, and can we also bring Atmanirbhar Bharat and Vikashit Bharat? How can we contribute? This is where I request all of you to think about it. With this, thank you all for your kind information. I am happy to take your questions. Yeah, any questions? I am happy to take.
Can you go back to that EIS? So here this 45 degree slope you said, which shows double layer behavior, and the other 45-degree line shows battery behavior.
No, 45 degree is related to diffusion, Warburg diffusion.
And that is not related to diffusion. So the other one after the semicircle, if it goes into a 45-degree line, that gives a battery behavior.
No, battery in the sense that typically when you take porous carbon material, you don't expect charge transfer. There is no semicircle in high frequency. You start with the diffusion and then capacitive 90 degree. But when you take battery type, what you typically expect is a charge transfer, because there are redox reactions. So high frequency to low medium frequency regime, that you have the charge like semicircle, because you know the Randall circuit parallel RC, and then further you will get the Warburg. Okay, so yeah, depends on the type of the energy storage system. Any questions?
Generalized question, not like about full electrochemistry or science. Thing is, we spoke about electrochemistry here, and then we spoke about half cells, 3 electrode system, 2 electrode system, and then batteries, supercapacitors. But science is related to engineering, engineering is related to business, and then business is related to politics. So, water desalination is possible. Yes, we spoke about ionic desalination possibilities. So all of these are interconnected, but where do you think we lag? What's your perspective on that? Yeah, I really want to know about that.
It's a very important and thought-provoking question. But my answer to you is, being a scientist and researcher, I would focus on my fundamentals. I would focus on my 3 electrode, 2 electrode measurements. That is where I have a control over the things. I can control the potential and I can measure what current I get. where I don't have control over the policies at a higher level hierarchy, which I don't really bother about it. But I'm only passionate about, or anyone doing here, like including Professor Martha ji here, and he has been like it's all about passion and get motivated from other researchers, and what is that contribution that you can make, and how can you train the students, right? How can you give knowledge to them, and how can you make a good citizens, like if you have the education, proper education, you are engaged in things, your mind will not think about other aspects. If you are not really focused, then always you can think of many other things. What is in our control, what we can control better way, we should always do it. What is out of control, and of course nothing is perfect. We can always keep on complaining and many things, okay, and everyone goes through this, okay, different stages. But what is most important is, let us focus on the thing and the task that we can do it. Of course, I am unhappy, I can always talk to someone and remove my unhappiness and express something, and I go play games and yell out everything. That always you do it. But being a scientist, we are not really that is super power that we have. We cannot do anything. Just we should be happy with what we are doing. So today I am happy with teaching. At least I will contribute to my teaching. At least some 10 people are happy with my teaching. I'm fine with it. And can I go and sleep nicely night? So that is what only I look for. And rest all things, of course I understand the things, and whenever there is a scope, whenever there is some possibility to influence the things, always I am there. But for that, if we have to go to that level, of course we have to do excellence in our lower level. Without doing excellence in the lower level, we cannot go. And you may say that some people are born gifted, and that's a different thing, okay, which again it's a matter of debate. But I would rather focus on where the charge is going and where ions are going, right? How to control them, right? How to understand, how to make new materials, how to make new devices, and what is that I want, right? I mean, take example of anyone who got Nobel Prize in battery chemistry 2019. Think about John Goodenough. He got Nobel Prize at the age of 99, right? Do you really think that he has been waiting for Nobel Prize? He was a magnetic, he was very famous in magnetism. He made a lot of oxides and things like that. What he understands the basics. Stanley Whittingham used titanium disulfide as a material. Then he understands, instead of using sulfide lattices, let me put oxide. Now whatever he developed in 1980s, so far we are continuing. Think about it, if he has not worked on it, by now you could have been lithium ion battery. Somewhere someone has to work, right? Not everyone will become famous, okay. But again, we should be happy with what we do, okay, that's all. And he could not control when he was going to get Nobel Prize. At the age of 99 he got, after 2 years he died, okay. But everyone admire him because he is immortal. Even he is not here, we respect. Like similarly Sir C.V. Raman, like he was a public servant, right? And in the evening he goes and does that experiments. It's a very, very weak phenomena, Raman. Everyone today, you tell me anyone is not calling this name Raman. Everyone talks about Raman spectroscopy. Even though person is not here physically, he is immortal. He is with us. How many people are acknowledging? Whole world is acknowledging. It is out of passion. I am telling you, it's all out of passion. And you have seen many unsung heroes also. That people have contributed a lot, but they have not been recognized. What to do? We cannot help it.
Also, एक बार टेक्नोलॉजी मैच जो रेडी हो जाएगा, तो कमर्शलाइजेशन के रास्ते तो खुल ही जाते हैं. I mean, once the technology is ready, maybe researchers, once they complete it, then all these politics, etc., they get sorted automatically. We shouldn't worry about that.
Yeah, that's also another good point, that things all automatically,
Fall in place.
And you know that even lithium ion batteries are commercialized. Still there are so many issues. You cannot operate at low temperature. You cannot operate high temperature, right? But still, edil mange more, that you want to do many things, right? Wow. Can I operate it at low temperature, right? Active research is being done. Can I make NMC or some other cathode materials, right? So it all goes on. That's what. There is no end to it. Okay, sky is the only limit.
And there is no right time also.
Exactly, there is no right time also. Okay, since you asked my perspective, sorry, it may be a little bit elaborated perspective, but I hope you get the point. Yeah. Any other questions?
My conception, like for a 4-year engineering course, sir, one of the course would be chemistry.
BTech.
BTech,
Huh.
BTech. So instead of being introducing an engineering chemistry, if we want to specifically introduce branch specific chemistry, say for example an electrical engineering student, what the topics will be opt to introduce in the chemistry subject. So for an electrical engineering, if we want to introduce the chemistry subject as branch specific chemistry.
Yeah, at IIT Hyderabad, if you ask me, only 60% of courses are related to their core courses. Any engineering you take, electrical, mechanical, these BTech students end up doing 60% of their credits in their particular discipline. Remaining 40% come from the general sciences, liberal arts, and there is something like left brain activity and right brain activity, and there are like lot of things that you can introduce. So for example, what we have is environmental chemistry is one of the courses that we give it to all BTech students first year, common course, which they get an idea about what is environment, how we should be respectful to the environment, and what are the things that are happening, and just to give an awareness. And also there is a practical component that students also learn by hands-on, that we have the chemistry practicals that are available, that they also do some credits. So as I told, you can also think about only giving like 60-70% of core courses. Remaining 30% can come from chemistry, physics, like basic sciences, and some 10 credits, 10% can come from the liberal arts, where a music, they can, one artist will come and sing a song, like dance classes they have to attend, and finally there will be an exam, right? So all engineering like mostly based on the left brain activity. So if you activate your right brain activity, then people can do marvelous things. So this is where I think you may watch some videos on YouTube. Our director, Professor B.S. Murthy, mentioned about this, how the curriculum has been designed to cater to the the students at the UG level, how their brain development happens by having different courses. You may follow or adopt that model.
So we do adopt, sir, like
Yeah.
go for learning, like as you said, for arts, science, engineering subject, core subjects, but in specifically when chemistry subject is introduced, what topics can be more
Yeah.
appropriate for electrical engineering students? What chemistry?
Exactly. One is electrochemical engineering that you can think about. Environmental chemistry you can think about. Environmental chemistry, sustainable chemistry that you can think about, right? So this way you can make some credits out of it. Any other questions? Thank you.
Hello. Wow. Shall we start or we'll wait for a few minutes? We are starting. Okay. A very good morning. Thank you. I hope you had good time this last 2.5 days. Must be tired listening to many talks. So I thought I'll give some general overview of lithium-ion batteries. So it can be extended to any battery systems. It's not lithium-ion batteries. It can be extended to any metal-ion batteries. So before going, just I wanted you to learn like what you do at we do at IIT Hyderabad. We basically are material electrochemists. We develop a lot of new materials. Our backbone is electrochemistry, like Dr. Narendra told. So we study the electrochemical properties in various applications, especially for batteries. So when you talk about batteries, we talk about lithium-ion batteries, sodium-ion batteries, metal-ion batteries especially. Then we work on a new concept called dual carbon batteries, where it's a sustainable approach where both the electrodes are carbons. Then we work also lead acid and lead carbon systems. So we are few in the country still works on this. Then recycling lithium-ion batteries and hybrid ultracapacitors. So what I have planned for today, so you will learn little bit. Dr. Narendra has already put in a systematic way to understand about battery chemistry. So I will give a brief overview of what batteries exist today, and then I will come to lithium-ion batteries. I will give you a fundamental of lithium-ion batteries. So the same fundamental applies to any metal-ion battery systems. So I will be talking about there are 3 classes of materials that have been used in lithium-ion batteries today. So that's I am going to talk, and then I will talk about how we prepare these electrodes. You know, the real electrodes I have this is the real lithium-ion electrode cathode, and this is the real lithium-ion anode. How we prepare them, and even how we synthesize this material also in the laboratory that I am going to speak, and then why lithium-ion battery fails, what could be the possible reason why lithium-ion batteries fails, and the safety features. Today we talk about some batteries are catching fire, some are very safe, which batteries are safe. That's also in chemistry wise I will talk about. I won't talk about in the device, a lot of device aspects. I will come with the material aspects mostly. So then I will give, if you want to do research, what materials you can really study in your laboratory. Basically, that's the goal of this ANRF pair. You know, we should able to help you to understand not only the topics, to improve the quality of research and extend the collaborations. Okay. So all you know, last 3 days you have been talking about energy. Energy is very important. So if you do not have access to energy, you tell you are not a developed country even, correct? And when you look at the India's energy balance, you see always you have high consumption and less production. That's why you are rely today when when some war happens, you always worry. You know, petrol is not available, gas is not available, and so on. So what we believe, the clean energy research is needed to solve these problems of such high magnitude. That's what we have been working. And if you look at the, many might have given about the renewable and non-renewable energy sources. So when you talk about renewables, we have non-renewable, we talk about coal, gas, or your oil, whatever, you have limited reserves, correct? And when you talk about renewables, we have few renewables today. We have geothermal, we have hydrothermal, wind, solar, and then biomass, correct? So among them, solar have been found to be very interesting and is available, and many we have been using. But again, and wind also in many places. If you go to Tamil Nadu, there are many places where you have wind power generations as well. And then, of course, other systems are coming up. So most importantly, then why you talk about energy storage? Because these systems are interpreted in nature. So today we, again, when you talk about solar, today a few years before government told 200 gigawatt of energy by 2022 or 2023, now 500 gigawatt by 2030 or 2032 600 gigawatt. We are going to achieve. But again, I do not want to go into details, so where they come from and so on. So the adaptability is very important. Still, we do not have a good adaptability today. And when you talk about, so these are all like now you have solar in your home and then you supply either you extra energy, whatever you are using, not able to use, you supply to the grid. That's very good advantage of a solar system, solar energy, using solar energy. So again, but when you want to use a real practical application, these are intermittent in nature. So we need energy storage devices to store this energy. Correct? Suppose we talk about EV today, electric vehicle. You have a solar panel which can the solar panel can be charged the battery at the present? No. So because you will have a small roof on the car which cannot charge this your 40 kilowatt or 60 kilowatt or battery pack. Okay. So anyway, so when you talk about then why batteries, Dr. Narendra was talking about Ragoni plot. Correct? When you see Ragoni plot, we have fuel cells, we have ultra capacitors, we have batteries. Correct? These are the three major power sources available today. Among them, if you see, batteries have a moderate energy and power. This is Ragoni plot, correct? Energy density versus power density. So those who are even don't understand, you see here. So it is energy density means how long I can drive my vehicle, and power means how fast I can drive my vehicle. Very simple way. Like if you see the the Jaguar has a high power, whereas Camel has a high energy. So whole day it can walk actually. So similarly, a marathon racer versus a Usain Bolt, So you see, that's always I explain with this. So energy. So how long you can drive your vehicle, correct? So that's your energy. So in one system, it's very difficult to get both an energy unless some other external devices is not clocked actually. So I do not want to go details. Fuel cells already he told, as long as you supply fuel, like suppose hydrogen oxygen fuel cell, you supply hydrogen, you supply oxygen, and you have a catalyst conversion of hydrogen oxygen into water, you get voltage. As long as the catalyst works, you supply oxygen, hydrogen, and you can get the energy, the voltage. Right? But again, you do not get really 1.23 volt in a fuel cell. You get much lesser because of polarization. That's what he explained. Similarly, again, supercapacitors. You do not see them in real life still because they are a bit expensive and viability is still not there. Right? When you look at the batteries, we have, you see, lead acid battery. Every home has a lead acid battery. You have an inverter in your home, you are using lead acid battery. It's very heavy, because the lead mass itself 207 gram per mole, and lead dioxide, which is another electrode, is 239 gram per mole. So they are very heavy. So energy density is, the density will be very, very low. So it is 30 watt-hour per kilogram. Then you are using in your like rechargeable batteries, that AA, AAA cells actually. These are all nickel metal hydride batteries. Okay. So nickel metal hydride battery, they have little higher energy than the lead acid battery, around 50 to 80. Their advantage is that they use their aqueous system, they are non-flammable. Toyota Prius or now the Innova High Cross has come, you see hybrid vehicles, they use nickel metal hydride batteries. Okay. Anyway, this is not completely related to those battery systems. So these batteries also came at the same time of lithium ion. But unfortunately, as they came with lithium ion has high voltage, energy and other things. That's why lithium ion has emerged as a leading entity as a power supply than the nickel metal hydride systems. So you see, lithium ion has high energy. I will come to that again. You don't have to again high energy. So today you see 250. If you see 1 kilogram, you take 250 watt-hour per kilogram. You can get 250 you can get with some chemistries, and where a lead acid is just 30, and nickel metal hydride is just 50 to 80. Energy density is very low. Whereas supercapacitor, again we talk about, they have a high power devices. So our goal is lithium ion, correct? So he showed about this. Just wanted to quick, how you choose the AC electrodes, how you define, how you got the lithium is high voltage. So he showed this electrochemical series. Correct? This is, everybody has seen this electrochemical series. Now it comes in, if you are studying in Narayana Chaitanya, it will come in the 7th class even. Okay? And I studied in intermediate. So you see the below, you have a lithium, which is a strong reducing agent, and fluorine is a strong oxidizing agent. If you combine, how much you get? E cell equals to 2.87 minus 3.04, you get around 5.92 volt. Then why such systems are not available? Because we do not have a good electrolyte operating at such high potentials. Now you can make that, we talk about ionic liquids or solid state electrolytes, if you can make, you can have those batteries. And another thing I want to tell you, if you see, this is all about periodic table. How many elements are there in a periodic table? 118 today. Let's consider 100. How many electrochemical cells you can make? You have 2 electrodes, one cathode, one anode. That means 100 C2 electrochemical cells you can make, correct? 100 C2. So what is 100 C2? 100 factorial divided by 2 factorial into 98 factorial, correct? So you get 100, you get here, how much you get? 100 into 99 divided by 2, you get 4,950. This is if you take 100, but we have 118. So that means more than 5,000 electrochemical cells you can prepare, correct? Clear, my friends? Correct? So more than 5,000 electrochemical cells you can prepare. But how many you see? You see lead acid, you see lithium ion, you see, so now we talk about sodium ion, we talk about nickel metal hydride, we talk about some defense batteries, that are silver zinc batteries, beta alumina batteries, and so on. Only hand counted. Why they don't exist? Maybe they are not compatible in the electrolyte, or the electrode materials are not suitable in the electrolyte, and so on. Great. That's why you have few systems. Great. You can make all. So another thing I want to just trace out here. So you have lithium. So today we talk about beyond lithium, not lithium, because lithium is only reserved in China, in South America, to some extent North America, and some part of Africa. And there is another element called cobalt, which is only available at Congo. And Congo, is a political tension country. You have child labor. So that's why people try to find out alternative to lithium and cobalt. So it is not there. So our Dr. Narendra also works on calcium ion. If you see extended electrochemical series, you will see calcium is 2.87, something like that, 2.87 volt. You have another one is potassium. Potassium has a 2.93 volt. Then it comes sodium is not written here. It will be 2 sodium to sodium plus, it is a 2.71 volt. So after lithium, that's why people talk about the sodium or multivalent calcium or the magnesium, because they have high voltage and the abundance. See, sodium you can get in seawater, right? So you can get a lot of sodium ions, but the way lithium works, sodium cannot work. You see the volume, you see the size. When a thin person walks versus a fat person walks, it just runs, correct? Who can run very fast? See, the similar way lithium and sodium also can work. Okay, but the way lithium ion batteries have been explored, sodium ion battery have been also explored, similar way. So I told you can use, So you see, these elements can be good as cathode, these are good as anode. You combine them, you get an electrochemical cell. And how the cell works, correct? I have I don't know, this is a lead cell. So my students used to prepare. So this is a lead cell, this doesn't work, this doesn't have electrolyte. You see, you have a cathode, this is the cathode, this is the anode part of the cell. And in between you have separator. You use separator to separate the cathode anode, otherwise you will have a short circuiting between them, correct. So, when you dip in the electrolyte, is not going to give the voltage. So, so what happen? Once you complete the circuit, the electron will flow from here, then you have ion movement. He told about electrochemical oxidation reduction reaction. Once you have oxidation reduction reaction, then that means the electrochemical series, then you will have the voltage, then the cell will work. Okay, this is how an electrochemical cell works actually. So, another important thing I want to tell you before going to lithium-ion battery. So, you talk about lithium has a high capacity. How you find that actually? You know Faraday's second law actually. 1 gram equivalent of material stores the capacity 96,500 coulombs. What is coulomb? 1 coulomb equals to 1 ampere into 1 second. You have to convert to ampere hour. Okay? So, that means 1 ampere hour equals to 3,600 coulombs. So, that means now 96,500 coulombs I convert to ampere hour, that means 26.8 H. One interesting observation, 1 gram equivalent of any material will deliver capacity 26.8 H. That means 1 gram of lithium will deliver this, gram equivalent of lithium will deliver 26.8 H, or 1 gram equivalent of sodium also will deliver this, and 1 gram equivalent of magnesium also same thing. Because remember, gram equivalent of sodium, lithium, magnesium, they are not same. What is the gram equivalent of lithium? Is 7. Correct? Is the atom, so weight by valency. Okay? So 7 by 1 is 7. Correct? And aluminum is 27 divided by 3 equals to 9. Correct? That means 9 gram of aluminum will deliver this much capacity. Magnesium 24 by 2. So that means 12 gram of magnesium also will deliver this, and sodium you talk about 23 gram of sodium also will deliver this capacity. Now is clear? Now I give you any element in the periodic table, you can calculate capacity. You know how to calculate the voltage from the electrochemical series. Correct? So when you want to do research, suppose XYZ has given a material, so first you calculate where the oxidation reduction reaction will happen. That gives you the voltage, and how much is the capacity of my material. Why I am very much interested in capacity and voltage? Because capacity and voltage is your energy. I want high energy. Higher voltage means high energy, or higher capacity is higher energy. So, okay. So this is a material which is used in lithium-ion battery. It is called lithium cobalt oxide. If you take its molecular weight is 97.87. That means 97.87 gram of this lithium cobalt oxide will deliver 26.8 H. If you take 1 gram of lithium cobalt oxide is 274 milliampere hour. If you take 1 gram of, so generally why we do like this? Because in the laboratory we prepare small electrodes like coin type cells for testing, and where capacity will be not even a milliampere hour, it will be 0.1 or 0.2 milliampere hour. Okay. So 1 gram of material if I take, it will be 274 milliampere hour. There is another cathode material which is used in lithium-ion battery called lithium iron phosphate. If you calculate, this is I think 156 is the molecular weight. So 26.8 divided by molecular weight. In the number of electrons you see, 1 lithium can be migrated. So you get close to 170 milliampere per gram. So this is how we calculate the capacity. There we calculate the voltage. Clear, my friends? Now already I told you what is energy. The capacity into voltage is your energy. So if you see lithium, the voltage is 3 volt, and then capacity is, if you calculate, 3860 milliampere hour. Okay, that means 3.86 ampere hour. So that means you will deliver, this is the energy, very high. Okay, very high energy. That's why lithium today is used in your in the choice of your all devices. So just a brief history of, you all remember he told also about Volta pile. Great. So, Alessandro Volta was the first to show the electricity produced by using copper zinc plates stacked alternately using a brine cloth solution. He used just copper zinc plates, and you see he was explaining the electricity generation to Napoleon in 1801 even. Okay, so he used copper zinc plates, that alternatively, like connecting them in series and producing electricity. And today we have the same concept of making batteries. Only battery chemistry has been changed. Instead of nickel, instead of copper zinc, today you use a material called NMC, nickel manganese cobalt oxide. It's called lithium nickel manganese cobalt oxide. This is used even in Tata vehicles or MG vehicles. And then you have graphite as the electrode material. So this is what I have in my hand. This is the real cathode, the real anode which is used in the lithium-ion battery. And you see this weight is about 430 kilogram. You see, again in the electric vehicle, if you see, your battery weight cannot be more than one third of your vehicle weight. So the vehicle weight is roughly, suppose if you take a SUV, it is around 1500 kilogram. The battery weight can be maximum 500 kilogram. So it clearly shows that. So you have close to 400 to 500 kilogram, and it consists of, you see, hundreds of cells connected in series and parallel. And you see here, he also used the same like cells connected in series to get the voltage. So when you want to make a battery, you connect them in series, you get voltage. When you put them in parallel, you get capacity. Correct? I hope you all know that. I'll come. I have a slide on that also as well. So now why lithium again? I told you, it has high energy density. That means it has high capacity, high voltage, and there is a self discharge. If you all have cars, correct? So you leave, you go for a vacation for a month, you come back fast, you give a jump start immediately. You think that your battery is discharged completely, or every 15 days you charge. For lithium-ion battery, there is no such systems. That means there is no self discharge. There is another called memory effect. Memory effect is only there in nickel-based batteries. What is memory effect? Very simple way I will tell you. So when you receive the cell phone, they tell you have to charge it. Right? You don't have to charge it, because a lithium-ion battery doesn't have anything. So why it happens actually? Suppose if it has come with 40% state of charge. State of charge means the capacity at that point, the total available capacity. So generally 5 ampere hour cell means only 2 ampere hour capacity there. So if you are using and then you are charging little and then you are using, so you are within the 2 ampere hour capacity. That is called memory effect. Memory effect is not there in lithium-ion battery. You can get your full capacity with a fully charged. So these are the main advantage of lithium-ion systems, and because of this, lithium-ion battery is the choice for your cell phones, camcorders, and implanted devices. And today you see even EV, electric vehicle, on the grid and many other systems. Correct? We talk about even aeroplanes, correct, with batteries. So that's why you see lot you have when you get down in the airport, you have, or even in the cities, we have Electra BYD buses, and we have MG, Tata, and then we have Mahindra, our leaders for the EVs today, and so on. We have next to IIT Hyderabad, we have a faculty. So he has this pure EV, this two-wheelers is manufactured here in next to IIT Hyderabad. Okay, this is a pure EV, in the name of e-Pluto vehicles. So again, very interesting thing. So we talk about EV, we talk about solar. Nothing is manufactured today, unfortunately, in India. This is the sad part of it. It comes from elsewhere, some different country. Okay, so I do have a EV program also, where the goal is I didn't bring. When you go to my lab, you'll see he'll show you 5 ampere hour and 30 ampere hour cells. With the help of these Japanese guys, we are developing some some cells, particularly for EV three-wheelers. This was there in the entrance, but I think it has been removed now. Correct something. So anyway, not to worry. Now still we have not come to lithium-ion battery. Let's understand what is really a lithium-ion cell. Okay. So now you see here, I told you this is my cathode and this is my anode. Then you can ask me, sir, you are not using lithium. Lithium, I told you, lithium has capacity, 1 gram of lithium will give you 3.8 ampere hour. What is your cell phone battery weight? It may be 20 gram. That means a pure lithium is not used in lithium-ion cell. Something else is used. So these are the lithium containing materials. One is called lithium cobalt oxide, another is called lithium iron phosphate. These are the two. Now cobalt is replaced with a, because I told you cobalt is expensive and even it's not thermally stable for a lithium-ion battery, but is one most important thing is very expensive. So cobalt people replace with lithium cobalt oxide. So you replace with nickel, manganese, cobalt. So it started with 1/3 O2. Okay. If you see, they have a very similar ionic radius, and then I'll tell you why the people are using. Then it went with the 0.5, 0.3, 0.2. This is the stoichiometric amount. The amount of manganese nickel is 0.5 mole, 0.3 mole, 0.2 mole. Okay. Now we talk about even it was in between 0.6, 0.2, 0.2. It's called 622. Now what I have is NMC 811. This is the latest. Some people are also working 9.5.5. So this is the 0.8, 0.1, 0.1. You see the content of cobalt is 0.1 mole. It has reduced from 100% to 0.1. But there will be lot of disadvantage as well. Okay, so here in this material, so cobalt is replaced with nickel, manganese, cobalt. Nickel will give you high redox and capacity, and then cobalt, I have a slide, I can just show you. It will give you the, this one. So cobalt generally used to give you, you see, structural, my friends. Okay. So cobalt gives you conductivity and structural stability. Those who are chemists, if you can calculate the octahedral field stabilization energy, this is a very this is strong. You have the octahedral stabilization energy is very high. This is minus 2.13. Means is the very stable structure. So it provides the structural stability and conductivity. Whereas manganese is cheap, it has also give you chemical stability. That's why all the mixture of the three has been used. But when you go to increase the nickel content, the capacity can be improved. You can get, but the thermal stability you get fire. Correct? Is because of low content of high nickel content, and or even you have a cobalt. Okay, because of that you get fire. The more nickel content you go, you will get good capacity but less structural stability, more fire. Okay, that can be another talk. If you invite me, I will give you on only NMCs. Okay. So let's come to the parent. Okay, so we have lithium cobalt oxide or lithium iron phosphate. This is here they undergo structural transition during charge discharge. That's not good. That's why you get heat in your cell phone if you have been using this. Whereas the lithium iron phosphate is a very stable material. So and you can see here the advantage here is voltage, and here is a less voltage. That means here you will get more energy. Here you will get more energy than lithium iron phosphate. Those who are chemists, you can see the LiFePO4. PO4 is a strong covalent bond, and it doesn't, oxygen cannot be easily released. Whereas here it can form CO3O4, oxygen can be easily removed. So that means why it causes fire? Because of oxygen. Oxygen is the fuel. It will ignite and it will cause fire. So that's why this material is the safest material. Lithium iron phosphate is the safest material in lithium ion battery. So I forgot also one more thing. I told you why lithium is not used and you are using graphite. Okay, you are using a lithiated graphite or the anode, because lithium form dendrites, they form kind of nail like structure during the charge discharge cycling, so it is not safe for the lithium ion battery. Okay, so that's why pure lithium is not used. You are using lithiated graphite, or there is another material called lithium titanate. Now people are focused, if you want to work future, you can use silicon carbon or a tin based material, alloy based material. There are conversion related materials, you can use it. So these are the cathodes, these are the anodes, and already Dr. Narendra also talked about the alkyl carbonate in lithium hexafluorophosphate is the electrolyte for the lithium ion battery. Carbonates, they are stable till 5.1 volt, 5.2 volt. LiPF6 is stable till 4.5 volt. This is the salt. It is required for the lithium ion battery. So what you see here, you see you charge your cathode. Basically, when you charge discharge, so you see here your cathode is getting charged from 2.9 or 3 volt till 4.3 volt. This is a NMC, you go till 4.3 volt, you see, and then when you discharge, you have lithium intercalation happening at 0.1 volt. So E cell equals, so you see here 3.9 or 3.8 minus 0.1, which you get 3.7 volt in a lithium ion cell. Clear, my friends? So these are the cathodes, these are the anodes, this is the electrolyte, and you see the cathode mass is coated onto this by using some binder. So that is called polyvinyl diphenylchloride, PVDA. Some people use sodium carboxy methyl cellulose. SCMC is a water binder. And then you see here another thing I want to tell you. So, and these materials are not very conducting. So we use some amount of additive called carbon black. We mix them thoroughly, and then we make a slurry and then coat onto the you see here aluminum foil for the cathode and copper foil for the anode. Why it is so? Aluminum is stable at high voltages. At low voltages, instead of lithium intercalation, it will be doing alloy reaction. That's not good. And this copper is stable at low voltage, above 3.4 volt it oxidizes. It is not good for the lithium ion cell. So that's why the aluminum is a current collector. What you see, the shiny portion is you are using in your home, aluminum foil. It is a electrochemical grade. That may be 95%. This is 99.9%. And another important thing I want to tell you. So the thickness, if you see aluminum and copper, this thickness is around 10 to 12 micrometer or 15 micrometer. This thickness is the aluminum current collector thickness is about 25 micron. This is because the conductivity difference. If you see the conductivity of aluminum is almost half of the conductivity of copper. That's the one thing actually. That's why the aluminum is thicker. You can have a feeling of the electrodes if you wish. Okay, so now most important thing comes here. So we have cathodes, we have anodes, we have electrolyte. So how the cell works? So when you charge it, the lithium from this parent compound go and intercalate between the graphene sheet of the carbon, and then you discharge, it comes back to the parent compound. The amount of lithium you insert and extract, that determines your capacity. If I am able to extract a whole lithium, that means 1 mole of lithium, that means a full capacity. That's what we calculate theoretically. Suppose lithium cobalt oxide, only half of the capacity can be obtained, only half. So that means instead of 274, you get close to 140. This is because of another reason even. So what I want to tell you, so the amount of lithium you extract, that determines your capacity, and the metal ion will give the voltage. The cobalt present or nickel present will give the voltage. Okay, so as long as you do lithium intercalation, the charging, discharging, charging, discharging. That means as long as they are structurally stable, you can make the cells will be working. If they are not structurally stable, you may get heating phenomena, and slowly your efficiency will, your capacity will reduce, your efficiency will reduce, and so on. Okay, I hope you all are clear. So these are the cathodes and these are the anodes. An electrolyte is a alkali carbonate in LiPF6, and you see here the cells generally operate between, if you see the lithium ion cells operate between 2.5 or 2.8 till 4.3 volt. Your cell phone, if you see, maximum maybe 4.2 volt in some cases. If LFP, if lithium iron phosphate, they operate 3.8 volt, is much safer. The voltage, because their voltage profile, if you see in the internet, 3.3 volt is they have they have platinum. Dr. Narendra also showed about lithium iron phosphate. Okay, clear, my friends? So this is the all about the lithium ion cell. Just wanted to tell you little bit of history of this lithium ion cell. He talked about good enough. So I told graphite is the anode. Always many people forget the contribution of Indians to lithium ion battery. Thus I wanted to tell you. You should listen to them. This is why this is how the lithium ion lithium. If you take pure lithium, this is how dendrites form. They can pass through separator and can cause the short circuiting. So that's why we are not using. So lithium intercalation to graphite was first shown by this gentleman, Professor Samar Bosch. When he was working in the Bell lab, he showed lithium intercalation into graphite. Many people, they do not mention about that. They mention about this guy who he presented in 1977 when he was working in the Bell lab. Later at the end of his life, he is no more. He came to IIT Kharagpur and died actually, so maybe 5 years before or sometime before. Okay, and this guy is a Moroccan resident, and he was working in some French lab, and he later, so this guy showed lithium intercalation from the electrolyte. This guy showed lithium intercalation from the lithium foil. That's the only difference. Okay, so he showed lithium intercalation into graphite, and then you see these are noble rates. So what is their contribution? Professor Whittingham, he showed lithium intercalation into titanium disulfide. Later to you are using molybdenum oxide, molybdenum sulfide and all things. These are all his contribution. And this guy, he's no more, he's more, my professor always says he's more than good enough. So he invented the lithium cobalt oxide and even NMCs, and later lithium iron phosphate. There are two Indian scientists along with him developed AK Padhi, Akshay Padhi, he is from Odisha, and Nanjunasamy from Tamil Nadu. He was his PhD and postdoc student, and Nanjunasamy was his postdoc student, and they developed in 1997 the lithium iron phosphate. That's what you have been using today in lithium ion cell. This is what I want to tell you, the Indians' contribution to lithium ion battery. So now how this guy came actually, Japanese. They developed technology. So you say Akira, you heard about conducting polymer. He was checking lithium intercalation into conducting polymers. So there is a guy Shirakawa who got Nobel Prize in conducting polymers in 2000. This guy was checking lithium intercalation into polyacetylene, and then later he got idea of lithium cobalt oxide of this guy and graphite lithium intercalation into graphite. So he combined both cathode and anode and made the full cell in 1991 using petroleum coke is the anode, and this is a propylene carbonate in DC, the lithium the solvent with some lithium salt in the electrolyte, and commercialized 1991. And today what we see very little difference in chemistries and the cells what we have been using and so on. Any questions you would like to ask, or in the end we can think of. So again I'll just skip. So if you look, lot of cathodes and anodes have been tested. So this is the main important. So now today we talk about NMC. This is the main important nickel manganese cobalt oxide or lithium iron phosphate, or there is another material called lithium manganese oxide spinel. So you can go, if you replace manganese with nickel, you can get to 4.7 volt. You have to charge to 5 volt. The spinel is a doped spinel, has the highest voltage. Just remember this. So doped spinel and lithium iron phosphate, instead of lithium iron phosphate iron, if you replace with other cations like nickel, you can get 5.1 volt. Instead of 3.3, If you replace with nickel, manganese you replace with iron, you can get 5.1 volt. Again, you don't have good electrolyte. You have to develop a good electrolyte. So what people have been doing, you replace with manganese. Manganese has a voltage of 4.1 volt. So which is within the electrochemical potential window of electrolytes. So people have been using lithium manganese phosphate or manganese iron phosphate. This is the next generation cathode material for lithium ion batteries. And then when you talk about, I'll just come again in a few minutes. So when you talk about anodes, graphite has limited capacity of 372. I'll come again. And people are talking about some alloy kind of materials and conversion type anodes. So like even silicon can give you 4200, even lithium itself. Now we talk about dendrite. Can you stop this dendrite growth? By some means, so you can use lithium even. Okay, so these are the targets now. You can work on these areas so to make good anodes. And when you talk about cathodes, you have manganese oxide, doped manganese oxide, or doped manganese iron phosphate and NMCs. These are the three class of materials for lithium-based batteries. I'll just skip it. So I told you lithium iron phosphate, correct? So in lithium iron phosphate, as you see, this is the voltage profile 3.3. If you replace iron with manganese, you will get 4.1 volt. If you replace with cobalt, you get 4.8 volt. The voltage profile will be higher. So that means higher voltage, higher energy. The area under the peak is your energy, right? And then you go to nickel, you get 5.1. So again higher energy. So that's and the advantage that they have a stable structure. As long so you can thousands of times you can intercalate and intercalate lithium without any structural change. That lithium iron phosphate and its discharge product iron phosphate, they have same structure. So that's the advantage actually. No change in volume, not much change in volume, and you can do lot of charge discharge cycling. That's why. And I told you phosphate is a very strong bond. PO4 bond is strong. Oxygen won't be released easily. So that's why it is one of the safer material today in lithium ion batteries. We talk about another material, lithium cobalt oxide. Already I told you, I don't want to go detail. So only half of the lithium can be extracted. This is based on the structure. Because if you want to see the chemistry, the oxygen band and the cobalt band overlaps. That's why you cannot extract a whole lithium because of the structural stability. Okay. So, but instead of cobalt, now people are talking about NMCs. And I told you what is the advantage of nickel, manganese, cobalt. Correct? Nickel will give you phase stability, capacity, cobalt will give you structural stability, thermal stability, manganese will give you chemical stability. That's why they have been using. And so on. I'll just leave these slides. Then another material I told just now, lithium manganese oxide. If you replace manganese LiMn2O4, this manganese with nickel, lithium, manganese 1.5, nickel 0.5 O4, you can get a 4.7 volt system. Again, still these batteries are not available because of electrolyte is one of the issue. Okay, you develop a good electrolyte, you can use this. Electrolyte is another good area to work. Clear, my friends? So this is how these are the materials what we have been using. That's the voltage profile you have. You see, lithium iron phosphate is 3.3, and when you go to manganese phosphate, you have 4.1. This is a manganese. So when you have a manganese and iron phosphate, you have around 4 volt, and this is the next generation cathode material. This Amar Raja is going to work with Goshen to develop this material. And there is another material which I told you, when you go to nickel 0.8, there is another material, nickel, cobalt, aluminum is called NCA. This is another cathode material which have been used by Tesla, but it has a low thermal stability. So again, already I told you, so this is what I presented, NMC 811. So capacity is 220 milliampere per gram. Then if you go to there is another material called lithium rich. This is nickel rich, this is lithium rich. You can get even double the capacity. These are the focus today. These are the cathode side. So again, remember 811 and LMFP, lithium manganese iron phosphate, or LNMO. This is a LNMO. I should write. I could have written first. So this is called LNMO. Okay, these are the next generation cathode material. Along with what are the anodes? So graphite, I told you, people have been working on. So let's talk about lithium. Is not used in lithium-ion battery. We talk about graphite. If you calculate the capacity, see if you see 6 carbon will accommodate 1 lithium. So if you calculate the capacity, it is 372 milliampere hour. You see, I told you the lithium intercalation potential is 0.6 volt. There is one tricky here. When you get your cell phone, it has been charge discharged at least couple of times, and there is a ACI which has been formed. It's called solid electrolyte interface. This is very important for the lithium-ion battery operation. Okay, so this is because of the electrolyte, electrolyte reaction. So what we tell, which happen at 0.7 volt, and then this is only happened during the fast charge, and it is done very slow rate so that you get a good ACI. The ACI helps not to degrade the electrodes. And after this, you won't get this. Only these two you will get. So if you see the anode side, you have 0.1 volt. Cathode side, if you combine with the lithium cobalt oxide or NMC, you get 3.8 volt. 3.8 volt minus 0.1 volt, you get 3.7 volt. Clear, my friends? So if you look, you can have alloys. So carbon is 372. If you see tin, silicon, these have high capacity. That's I told. You can use other materials to develop high capacity. Again, high capacity means high energy. Suppose if you can make pure silicon, silicon make active. Today silicon 10% is used or 20% used. You can use 100%, 4200. Instead of 372, that means 10 times you are increasing the capacity. Similarly, if you can increase the capacity of the cathode, you have a cell phone where you don't have to charge for 10 days. So that's the goal. Great. So if you see, silicon is an attractive material. So you see 6 carbon will accommodate 1 lithium. You see one silicon will accommodate 3.75 or 4.4 in some cases. Tin also will have 4.4. That means high capacity. So now I'll just give a brief how you make this material. You all ask me, sir, I do not know how to make these materials. I told you all these materials. There are a lot of synthesis approaches available. If you read, they call solid state method, sol gel method, so then solvothermal, hydrothermal, then they call co-precipitation. There are many methods available. I'll just show you, there is a called combustion method where you can use sugar as a fuel, and you can burn in your kitchen, and then you heat. If you have a furnace at high temperature, you can make these oxides. But for carbons and this phosphates, you need a inert atmosphere. For oxides, you can do any this kind of furnace you can do. So I'll just show you a video. Suppose I want to prepare. This is a cathode material. So I will take 1 mole of lithium. So I want to prepare NMC 811. I'll take 1 mole of lithium precursor, that is lithium carbonate or lithium nitrate. That is 0.8 mole of nickel precursor, 0.1 mole of manganese precursor, 0.1 mole of cobalt precursor, and in some fuel, and mix them thoroughly, and then I'll cook it. So you'll see, you have seen by mistake sometime if you have made sugar syrup and then it has charred, you might have seen some, it becomes a kind of foamy, then become kind of like this, like then they become like this syrup liquid, and then become foam, and then it will catch fire. You can get really good nanomaterials, but that doesn't work, that doesn't have good crystalline structure. If you heat it, then you get it. I have a small video, you can see it. I do not know. We should try to complete by, okay, I'll try. What is the time? 12:30, okay. I'll try to complete. You see here, I have taken all the mixtures. This is what in India students do in the lab. Many students do in the lab combustion synthesis. So you just heat it. You will see that once it catch fire, one point, then it whole mass cell catch fire. Then you bring it, grind it and heat at a desired temperature, you get your crystalline material. You will get in YouTube. Okay. So we used to do like this. Once I prepared 500 gram 100 times maybe, or maybe more than 100 times I did like this. Taking a sand bath in just a hot plate you can do it. Our students do in an oven, because oven has a uniform temperature. But you can do on a hot plate even. So already I told you in the beginning, you see, once the material is prepared, so material you synthesize, then you characterize. That's I forgot, I didn't put. You have to know whether the proper material have formed. So how will you know that? X-ray diffraction, right? You study the structure of the material. If it not formed, then you keep on heating. You may have to increase the heating temperature and so on. And to see the particle size morphology, you have to do SCM. And maybe stoichiometry, you want to know, you have to do ICP. Right, intertypical plasma, so that what is the, like I have 0.8 mole, 0.1 mole, 0.1 mole, how I will know that? So you have to do the composition analysis, correct? Once it's done, so I have to prepare the electrodes. I have now, see, I know basic, now I can prepare any material, correct? Now I know how to synthesize the material, I know how to do the structural analysis, now how to make electrodes, correct? So I told you, you take in a solvent, you mix this material along with the carbon black and PBDF. PBDF is a binder, carbon black is a conductive diluent, you mix them. So generally carbon black you can use 10%, industry use 2 to 3%, but in our lab and all we use 5 to 10%, and binder 5 to 10%. Then active material, positive active material, negative active material, like this or graphite, we take 80 to 85%. We mix them thoroughly with a mixture. We have mixtures available, and then we do a coating with called Dr. Blade. The students have already, few students who are working here, they have already experienced. And so this is a coater, and then I told you, you see, this is the real electrodes, and I do not know whether I have here. Electrodes I think I didn't bring, but that's I showed you anyway. You punch it that, correct? So you see same thing, correct? I told you that, and then you see here, you want to, the coating generally what we do actually for high power is different. High power means it should be thin. High energy means more loading of material. So generally we do in our students, see, commercially today they do 40 to 50 milligram per centimeter square. Our students, when you take a 5 milligram, they are tired. Sir, they think like what is a big task, correct? Priyaranjan, at least 5 milligram it should be in the lab scale for the cathodes, for the anodes minimum 2 milligram. Otherwise, those who are doing 1 milligram, I really get frustrated. No, you don't get frustrated, I get, error is very, very high. Do not do that. You want to learn something, you have to make thicker electrode, and this is how, if you know how to make a good electrode, it is 100% going to work. I have made 10,000 cells during my postdoc. I think, the whole group here who work on lithium-ion battery might not have prepared, and believe me, it all work. 1 gram of material I will grind and make slurry and coat it. Not you all do 50 milligram. What is the PBDM quantity? 10 milligram. Your balance has a 2 milligram error. No, don't do that. Try what sir is trying to tell you. Don't do such mistakes. Take at least few hundred milligrams of material, make a slurry and coat it. I wasted a lot of materials. I never did, believe me or not, never did less than 1 gram of material. You have a good coating, then you do the good drying, then you do the calendaric, never exposed to air. Try to avoid exposed to air or the electrode once it is dried. Okay, and you can see the thickness of this thing by using a cross-sectional SCM. And then I told, Dr. Narendra told how to choose electrolyte. You can have, now we talk about non-aqueous here because it has to operate 4.3 volt. some cases 4.7, 4.8 volt. So it has to be non-aqueous electrolyte, no water-based electrolyte. Water decomposition potential is 1.23 volt. We cannot use it. Right? So non-aqueous electrolytes, the best electrolyte is GCDECl LiPF6. You can use polymer electrolyte. Now today people talk about solid state electrolytes even. Ceramic electrolytes where the but again conductivity should be one of the is the issue. So you have to improve the conductivity, which should be close to this. Okay, there are several. You can have gel electrolytes, you can have gel polymer electrolytes, you can have solid electrolytes, you can have liquid electrolytes. Okay, and you can have ionic liquids. These are all listed here. This is ionic liquid. This is listed here. This is a polymer electrolyte which your LG is using. This is what generally it is used. Again, so these are the most important characteristics. Not only conductivity, voltage stability. It should not be flammable. Electrolyte is the main culprit for catching fire of lithium-ion cells. It's a highly flammable organic electrolyte you are using, and when oxygen comes out, you have a fuel, it will catch, when the temperature goes close to 80-90 degrees centigrade, that's it. It is going to catch fire. So we use a separator in lithium-ion cell is called, you see I have here you see here a sodium-ion cell, here you see polyethylene polypropylene here. This is the real cell what we developed in collaboration with someone. This is a 20 layer of cathodes and anodes are there. I may have another cell here. The real commercial cell what we are trying to do. This is a 5 ampere hour cell you see here. Okay, this he does all things and we have been very successful. These are of course this is assembled in Japan, not here. And we get like this, we fill electrolytes, do the formation, do the durability test. We have been successful. Yesterday we submitted the report. Let's see. So this is you can have a look. So it is a 5 ampere cell. When you come to my lab, you will see 30 ampere cells. Please. Please.
Maybe in the workshop tour, can we see your team building a lithium-ion cell? Maybe 1 volt.
Sure. Can you just yes, one person can show pouch cell, one person can show coin cell. Okay, so this is the next what comes actually. Already I told you current collector what is the size. If you want to high energy, you have to have 100 micron thickness, 60 to 100. If you have power, very thin. So this is what coin cell paths. So they are going to show you this. So the bottom part, top part, and then you have you do not have. You will see all the things in you go to lab. Even Dr. Narendra has same facility. We have all have same facility. Oh, sorry. Can you? So, can you help them to see, the bottom part, top part, and this thing? So you see here we have a top part of the coin cell. This is the bottom part with a O-ring. This is it. You see, this is the bottom part. This is the O-ring. O-ring is used to separate between the bottom part and top part. One side you can use, this is there cathode node, no anode. So in the lab you will see cathode anode. So we put a spring, so that we put a spring, is here, you see here, same thing what we have here. Put inside, we put a spacer in between. You put a spacer, so we have a spacer, where it is a spacer. Then you have cathode anode, which I am not brought here. In between you put a separator soaked in electrolyte. Then you put the top part. We have coin cell crimper, and you can just and crimp it. We can make hundreds of cells per day if your cells is working. Okay, you all know now how to make a cells. These cells are easy to make, but not easy to make. This looks big electrodes, but it doesn't work just like that. You have to give lot of pressure. This guy is going to present you, Hari Prakash back. He is going to present you this pouch cells. It doesn't work just like that. It needs lot of effort. It needs a pressure. You show the facilities what we have. So you have made a cell. You see, we get all cells like this. This is called 18650. 18650. What is 18650? I didn't have, battery course I gave 42 lectures. battery supercapacitor. So I am trying to complete in one lecture. So this is called 18650 cell. What is 18650? The diameter you see here is 18 millimeter. 6.5 centimeter is the height. This is called, what you got is CR2032. CR2032. C stands for anybody. C stands for lithium. R stands for round. Okay, this is round. C means C, lithium. Even it is Cr, that means it is 100% lithium cell. R for round. 2032. The thickness you see 2 millimeter. So 3.2 millimeter is the thickness and 2 centimeter is the diameter. CR2032. In the shop you will get 2016, 2025, 2032. You see. So based on even if you have a balance which is a CR2016, if you take this 32 is not going to fit, it is not going to work. So you have to take particular design one, because the space inside is important. If it is too thick or too thin, then if there is no contact, then it is not going to work. So always make sure that you use the same CR2032 or 25 or 23 or 26. Okay, so you should have, correct. Now I have a cell. If you see your laptop is written 11.1 volt. How you get that? That means 3 cells are connected in series. 3.7 plus 3.7 plus 3.7, you get 11.1. Correct? Okay, and when you connect them in parallel, you get the capacity. Clear, my friends? When you, suppose it is a 2.5 ampere cell, if I want to increase, that means all positive together, all negative together, that is parallel. When you see positive to negative, negative to positive, you connect it like that, that is series connection. Okay, that means voltage will be added. When you have parallel, the capacity will be added. Clear, my friends? So when you see the stack, the battery stack in your EV, it consists of hundreds of cells connected in series and parallel. It's called PCM and SCM. You know, series combination module and parallel combination module. PCM and SCM. Anyway, you need a lot of apparatus to do this and study. Okay, so you will see all the things. This is a ball milling machine which makes everything. You have this is a furnace which synthesize. This is again a furnace which synthesize. This is a vacuum chamber where you dry the electrodes. This is where you make electrodes. This is a calendaring machine. This is a power sealing machine. This is a coin cell crimping machine. And all these operations need to be done either dry room or glow box. Because lithium, once you expose to air, it will form lithium hydroxide, lithium carbonate and other things. One lithium cell form is not going to work. Right? And electrolyte also will react. Clear, my friends? So, and these are testing equipments. You will see all the things in Narendra's lab and my lab as well. And first, once you make the cell, always, if you ask me, first I will do a impedance. I do not know whether my students do it or not. First I will do a impedance to understand about what is the ohmic resistance, solution resistance. That's important. And then I will do a cycle voltammetry. He told already. You do whether where is the oxidation reduction is happening. That's important for me. This will give you the cutoff voltage of the cell. How this designer had told that 4.2 volt. This is based on this. Your lithium iron phosphate is going to work 3.8 to 3 volt. This is the CV which you told. Correct? Correct? The oxidation reduction reactions are happening in this cell. Then another thing. We do a C rate analysis. You tell how you know that your cell phone is charged in 1 hour. And it is working. So generally what we do actually, so we apply different current. So 1 C refers to the capacity in 1 hour. Your cell phone is a 5 ampere hour means if you pass a 5 amp current, it will go for 1 hour. So 5 ampere hour capacity is time into current. So your IT current is 5 ampere hour. So 5 amp current is passing. If it is 2 hours, that is 2.5 amps current is passing. That is C by 2. If it 2C, 30-minute charge discharge, we talk about fast charging. How it is possible? It's because the material should be able to capable to take charge also. 2C means 30-minute charge discharge, 30 minute. 5C means 12 minute. Like 10C means 6 minute. Clear? C by 20 means C 20 hour. In your night hours, next one is telling you do charge of 8 hours or 10 hours. That is C by 10 charging. You know, slow and steady wins the race. You go slowly, you can walk, you can reach your airport by the morning. But if you run, you will get down at the highway somewhere, correct? It's like the same thing. So like slowly if you go, you can accommodate, you can get more lithium into the graphite. So you can get more capacity and life is better. At high rates of charge is not at all advisable for lithium battery. You will cause dendrites. That's what I told here. Low temperature also will cause dendrites. So these are the, like high rates are not good. Like you tell 10C, no, there are some chemistries 10C is good. I'll come to that in next slide. So you are clear, my friends? Sorry. So another thing, you got C rate. And let's see. This gives you, if my cell is not working at 10C or 5C, you see this gives me a voltage profile. This is my operating voltage of the system. If you have a 320 volt system, suppose you have connected something 300 cells, 320 volt in LFP cell. But when you apply 5C or 10C, the voltage is reducing. That means it cannot go. So this gives you the information about at what voltage your vehicles is going to run and what current you can apply for charge. Okay, and one charge, one discharge is called one cycle. As long as it is very stable, the Coulombic efficiency, that's what I told, or Faraday efficiency is 100%, 99.9 is very good. That means whatever charge you are giving, you are getting. So that's good. The life will be better. Quickly, I'll go. So there is a system with LFP and LTO. You can charge quickly in 15 minutes, 10 minutes, because they are zero strain materials. Whereas, and you will, but a problem with that, this has a high voltage. This is a 3.4 minus 1.5, you get 1.9 volt. Here you get LFP with graphite or NMC with graphite, you get 3.3 or 3.7 volt, but not the fast charging. Not fast charging. Next one in some models gives this one, and not lithium cobalt oxide, NMC 532 or 622. 532, that is the common. 811 is not used. Okay, clear, my friends? So this is you want to discharge thousands of times, 10,000 times. People have demonstrated with this system, particularly mining trucks. Where you don't have a space limitation, you can have less energy, but you can discharge 10,000 times. Every day, 15 times you can charge it. Correct? So anyway, I'll just leave it, this one. So then you can ask me why the cells get heated up and all things after some time. So again, I'll discuss briefly. So these are like what happens when you have oxides basically with all with electrolyte. What happens? They form, this is a alkyl carbonate, this is LiPF6 salt, and if you have some amount of water, you will form PF5 and HF. They are not good. These are some chemical reactions happens on the surface, and surface become thick with time. So so this is one of the main reasons. So when it is become very thick, so what will happen? See, if this become thick, so what you see now, electrons were easily flowing. Electrons and electron was easily flowing, and ion was easily moving. Now when it is thick, you see it's an insulating layer. Can electrons tunnel? No. So insulator. So then when you are charging, so what you are doing? So it is coming to the high voltage. So suppose after 3 years or 4 years, within 10 minutes my cell phone is getting charged. So, but some current is passing. That current is making joule heating. That's why the cell phone is getting heated up. It is not charging the cell phone. It's just making the current is I square R, joule heating. So because of joule heating, the cell phone is getting heated up. So it is not because, so again electrolyte also dries out because of heating. And when you have a lot of heat, even LFP cells, even bulge, you can show the LFP cells which are bulging. In our lab you can see, it is very surprising also. We have till 100 ampere cells. So this is one, and I'll just leave it. This impedance rise and all SEI. I will stop. This one I'll just go. So already I told you, among NMC and LFP is a safer material because phosphate bond is very strong. Oxygen cannot be easily removed, and they are structurally stable. Whole lithium can be removed from the lithium iron phosphate, whereas NMC, you see, still half of the lithium stays. I told you half of the capacity of the lithium is staying is not good, and oxygen can be released from the lithium cobalt oxide or NMC. Oxygen release will ignite the fire. So oxygen release is the first major drawback which causes the fire. Okay, so this everything I have written here. So one is first is oxygen release, structural instability. Half of the lithium still stays in lithium NMC. That's why NMC is not a thermally stable cathode compared to LFP. And this has been proved. I'll show you in the next slide the thermal stability test, which is called accelerated rate calorimetry. This was done by professor. My Israel professor used to do a lot of things. This is called NCA, lithium cobalt oxide. Is next. Even NMC concepts are here. You see, 180 degrees centigrade is the onset of a chemical reaction, a vigorous reaction. If temperature goes from here to 180, immediately it will catch fire because you see the amount of heat will be more. You see LFP, the red one, is 60 degree higher than the NMC. So LFP is a safer material. That's why people adopt. And when you don't have a good BMS like in two-wheelers, in India if you see, two-wheelers doesn't have a good BMS, whereas four-wheelers have good BMS. Why have you heard about your car has caught fire? No, whereas the two-wheelers caught fire. This is because you have a faulty BMS, not a good BMS, which is installed in the two-wheelers. Correct? So that's why like lithium iron phosphate is safe. Is very safe if it is there in your vehicle. So today again I have already told all about what are the cathodes, what are the anodes we are going to use in the next generation cathodes anodes. So other than this, what people try to work, I told sodium, magnesium, calcium. This is multivalent redox couple that people are working. Lithium air batteries also people are working. Lithium sulfur battery people are working, and there is a called redox flow batteries also people are working, and liquid metal battery. These are all alternative battery systems are coming other than lithium ion batteries. Okay, so I'll just show 1-2 slides what you can do. So what we try to do, we develop nanomaterials, but nano is not good for health for the battery. Nano can move very fast. Okay, you can do a good charge discharge, but you see nanomaterial I want to load on the cathode. How much nanomaterial will load? Very small amount. The loading, the tap density will be lower. Many of you are mechanical engineers. The tap density will be lower if you put nanomaterials. If you put micromaterials, you have good tap density. So what we try to do, the primary particles are nano. Like pomegranate you have seen, right? Pomegranate primary particles, just a second. Primary particles are nano, that seeds are nano, whereas pomegranate itself is a micro. So that's safe. That is called engineer is by co-precipitation method. That is one of the way to improve the material tap density. At the same time, we do some electron conducting layer on the surface to improve conductivity, and also sometimes some lithium conducting layer to improve lithium ion mobility. Of course, like doping also we do. These are the areas you can focus to develop the materials. So other than these materials, there are some materials called, I told you already, the phosphates. These 4 I told you. You can, other than phosphate, you can talk about silicates. It should be cheaper material, correct? Silicates are very good. You can use silicates, but silicons, they are insulators. So how to improve conductivity? And they undergo a lot of structural changes. Then it is not easy to develop these materials. So you can focus on this material on the research aspect, not on the like device aspects at the present. Similarly, you have fluorides. The iron fluoride is a 3 electron transfer. What I showed, 1 electron or half electron. This is a 3 electron. It can go to iron 0 and LiF 3 electron transport. That means 3 time capacity. Even organics some people talk about, but organics doesn't like organic. That means organic cathode will dissolve in organic electrolyte. So you have to, it may be good for aqueous, but aqueous again voltage will be low. So you have to find the electrolyte where this organic cathodes will be stable. Electrolyte is one of the integral part of the system. So these are the areas cathodes you can develop. I told you also anodes like tin, lithium, lithium in the lithium metal batteries, and then you can silicon also you can work, tin also you can work, all these materials you can work. Other than this, I told you recycling is very important. Correct? When you talk about sustainability aspects, we do not have lithium source, we do not have nickel, we do not have cobalt. Correct? We all depend on elsewhere. So recycling is very important. So you can focus. So even graphite, do you think graphite is produced in India? No. Even we have graphite India, Tata, many are what have graphite, Birla Carbon, many companies are there, but battery grade graphite is not produced still. So battery recycling, all aspect, cathode, anode, all recycling can do. We mostly focus on the anode part. Now we have started on the cathode part as well, because we do not recover the metals. We recover. Can I use lithium iron phosphate or lithium cobalt oxide again? There will be some lithium loss. There will be some other metal loss. How to recover that? So we try to do that. So with this, I just wanted to summarize what I told. Today, I just talked about a brief overview of, I gave a brief overview of lithium ion batteries, starting from the history to development of lithium ion battery, to electrochemistry, then the cathodes we talk about, the anodes we talk about, then how we can synthesize this material, how we can make electrodes, how we can make cells, how we can test them by galvanostatic charge discharge, impedance, cycle voltammetry. These are 4 important tools. Then how degradation occurs, then how thermal stability reduces with cycling. That's we discuss in this lecture. And even I told what are the cathodes, anodes you can develop if you are interested. And with this, I just wanted to thank these 2 gentlemen who taught me. Of course, there are 2 more people. He is Professor Shukla from ISC. He taught me the aqueous electrochemistry. My background is pure battery. He taught me lead acid battery, where I have worked with an industry called NED Energy Limited here in Hyderabad. 7 years, every quarter I used to come to Hyderabad, and I can develop even large scale lead acid batteries if I get an opportunity. Okay, even we have demonstrated already. And then Professor Darren Orbach, who taught me how to develop lithium ion batteries. There is another few people also who also gave me future direction of lithium ion batteries. So when I joined here, I started lead acid batteries and lithium ion batteries, and then slowly we extended to sodium ion batteries and supercapacitor and recycling lithium ion batteries. So I have about 20 like a PhD and MSc and postdocs in my group, and couple of pair students have joined with me. She joined a few months, a couple of weeks before, and forgot your names. So Radha and Harsh joined with me. I want to help the PhD students so that they grow. So that's the motto behind it, and do well, wish you all the best, and let me know. It is not today's talk. You can get back to me whenever you want. You can call me. I'll be happy to come and again interact with your students if needed. Okay. Thank you and welcome for any questions. Government is so on the critical minerals people have they have been working. critical minerals. So they have established, I think, 3 centers. IIT Hyderabad is one of the center where they are working on critical minerals. As far as lithium-ion battery is concerned, lithium, cobalt, nickel are the main important things. Nevertheless, graphite also can be covered. And there are several companies also working on this. Even there is in Hyderabad itself, we have Nile Limited, who is the biggest recycler of latest battery. They are working on lithium-ion battery recycling as well. So this is initiated, but again, it's very strange. Only 5% may not be recycled today. 95% is thrown. That means you just see, I told you, it contains fluorine. So the fluorine glasses may evolve when you burn it. And you burn also a lot of raw materials, precious material like cobalt. Somebody sometime before told, instead of investing gold, you can also invest cobalt. And we are throwing into the garbage and burning. So I do not know how far it is good. And still, we India lack in both lithium-ion batteries production and recycling as well. It may take a few years to come. People like Exide is working vigorously, so they may have soon you will see the lithium-ion battery from Exide. Amaraja have been trying for several years, but I do not see any progress still with the Gosan. They were trying, but I do not know. And of course, lead-acid battery is not going to die. Lithium-ion battery will stay. It is also not going to die in our lives. So they will be kind of a part of our daily routines. Like you tell lead-acid battery, lithium-ion battery also will stay in our lives. Even though other chemistries will be coming up, but nobody will beat lead-acid battery on cost grounds, and lithium-ion battery on kind of what we talk about performance, whatever energy we talk about, maybe. So, tell me.
Sir, we have talked about the PO4 mode that is helping the batteries. Sir, in sulfur batteries, in sulfur batteries that we are.
Okay.
So if you make a sulfate bond, will that be exactly?
You have a polysulfide shuttle in lithium sulfur batteries, correct? That has to be mitigated. Where you are trying to make sulfate bond, can you tell me? You have a pure sulfur, correct? Or carbon sulfur. That has to undergo polysulfide shuttle. How you are stopping, that you have to see. So if you can make really, then but again, that sulfur should you have you are talking about your conversion reaction, how it can accommodate lithium. Whether sulfates are why sulfates have not been used in lithium-ion batteries much. It has been demonstrated by good enough in 1985, but there again they are not good conductors again. When you talk about even phosphates are insulator, kind of 10 power minus 18 to 10 power minus 14, and sulfurs again below. When you talk about lithium sulfur, you have mostly carbon, which is 10 power minus 30 Siemens per meter, correct? So can you develop? Maybe it will be stable. The polyanionic network will be stable, and you should able to. The goal is to lithium insertion or whatever like a lithium reaction. Will it be able to accommodate lithium? If not accommodate, then how will we be able to get capacity? The framework is very stable. That's why you get a very stable network of lithium iron phosphate. Similarly, sulfate also has a polyanionic network which will be similarly stable. Maybe similarly stable.
So apart from the spinel structure and the orbital structure that we have discussed, what other structures can be stably used for the
So I told you layered structures, even NMCs, people who are working on 911. But the problem is that when you increase the nickel content, the thermal stability reduces, capacity increases, but thermal stability reduces. And the structural instability increases. So that means you have a rapid structural change, which is not good for the health of battery. Structural change needs to be mitigated. So that's another important thing. Okay. Anything else, please? Or we can discuss during lunch also. Okay, so I'll be available when you visit the lab, and if any questions you can ask me. Okay, thank you. Have a good day.
So, I would like to invite Dr. Ganeshwar to facilitate Professor Martha.
Thank you.
Thank you for your talks.
Thank you. Thank you. Thank you. Thank you.
Thank you, sir.
I hope it was okay. I tried to complete in 1.5 hours. Thank you.
Nagesh from JNT, Kalkiri, that's close to
Did I give my card?
I'll put an email to you, sir.
Okay, good afternoon, everyone. So this is the last day of this workshop. I hope you have some learnings on this area. Um, Hands-on session as so. Of course, little rescheduled, and earlier it was 2 to 3:30, and maybe now we are starting at 3 o'clock. And I have to leave also at 4:15 maximum. So I will try to excuse it. Mm. So today I will be talking about lithium-ion batteries. You might have seen in the morning. I think Professor Martha might have discussed about it. Uh, but I will be talking mostly new energy systems which are beyond the lithium-ion batteries. We all know lithium-ion batteries. We are working. We are using them in our day-to-day mobile devices, then laptops, right? Of course, electric vehicles also have the many of these Tesla-based cars. They are using the lithium, battery, right? Uh, but their and batteries they have their limitation. We all know that even the electric vehicles which we are using these days, they have a run cycle, right? Go up to a limited distance. So there is always a need to look for better systems, better energy storage the requirement in terms of electric vehicles, for example, which and in fact the cost wise also, if you see today's electric vehicles, half of the cost of the electric vehicle is because of the battery, right? So there is always a continuous need to improve the energy density, power density of these energy storage systems. So we are looking for advanced energy storage systems which are not just limited to the lithium, beyond that, okay, lithium ion. So today I will be talking mostly two examples. One is lithium sulfur battery, and another I will take metal CO2 or lithium CO2 battery, which is very lithium sulfur battery. I would say the research started a few decades before, but still it is not fully commercialized. And we will discuss what are the challenges. And then, of course, the very new chemistry of batteries, which are metal CO2 batteries. I will briefly introduce that as well today. So if we see work group at IIT Hyderabad, which is known as Carbon Lab, we work in different energy storage systems. Of course, we do work in the lithium-ion batteries, but at the same time, we work in the metal sulfur batteries. So not just only the lithium sulfur, but also sodium sulfur, potassium sulfur, because we know that lithium is having a scarcity in the Indian context, especially. Then we are also working on supercapacitors, hybrid ion capacitors, where hybrid ion capacitors where one electrode is like battery, another electrode is like capacitor. And then we also, last few years, we are working in metal CO2 battery, which I will briefly discuss today. So now coming to the uh, advanced energy storage systems, as I was telling you, that in India, we are looking for electric vehicles, and there is a mobility mission from the government of India where we want to go for maximization of electric vehicles by 2030. And we are expecting around 31 million electric vehicles in the country by 2030. So obviously, the lithium-ion batteries are not the future, right? They are having limited energy density. Even the lithium is on the scarcity. So we need to look for the energy storage systems which are having much more energy density, much more power density. So this is something like a motivation for us to go beyond that. And in fact, this Reagan plot, I'm hopeful that might be discussed by Professor Martha also. So if you see, the Reagan plot is basically the energy density versus the power density or specific energy density volumetric. So lithium ion is there, and then you can see lithium sulfur and future lithium sulfur. So we are looking for batteries in the future which has more power density as well as more energy density. So lithium ion battery is not really fitting into that. Uh, to understand in a very crude way what is energy density and power density, for example, uh, let's say you want to run a battery, let's say electric car, uh, how long you can go with that car, right, in one simple charging. That is defined or that is governed by the energy density, right? Let's say if you have high energy density, which means you can go continuously for more kilometers, more distance. But if you want to accelerate your vehicle, right? For example, if you want to climb up some slope where you need power, there it is called power density, right? How fast you can get the power within no time, that is density. How long you can go, that is energy density. So in order to go for electric vehicles especially, we need high power density as well as high energy density. And that is where we are looking for these energy storage systems which are more futuristic rather than batteries.
So power density means case of trucks, more load they have to pull and increase
Load as well as the more power you need. So see, if you're consistently going on a planar path, right, you don't need power that time. It's a energy density. But if you are climbing, if you are accelerating your vehicle, if you are starting the vehicle, there you need more power. So basically, I would say the future is not really electric vehicles. Future is hybrid vehicles. Okay. Even sometimes it's a battery and supercapacitor combination, because supercapacitor gives you the more power. Supercapacitors are known for more power. Of course, one way is you look for the batteries which are having high energy density and high power density, but of course there will be always a limitation in terms of power density. So another way is hybrid vehicles, where you are looking vehicle batteries and supercapacitor combination, right? So switching over. Uh, Sometimes even nowadays new device which is called hybrid ion capacitor. I mentioned in the first slide, we work on that. So where one electrode is working as a battery, another electrode working as a capacitor. So these are the future possible directions, right? So, well, very crude comparison in terms of lithium ion batteries and lithium sulfur batteries, for example. So, as I mentioned, the driving range on an average lithium ion battery, let's say 300 kilometer, then lithium sulfur can go 600 kilometers. Given all the conditions are same, right? These are the idealistic comparison. In terms of cost, other way around. So lithium ion battery cost is 151 US dollar per kilowatt hour, and lithium sulfur is 65. And then the energy density, which is more important, lithium ion 300, lithium sulfur 2600. So in all the factors, whether it is a driving range or more energy density or the cost, lithium sulfur battery is definitely having a much more advantage than the currently used lithium ion batteries. But of course, at the same time, there are certain possible reasons by which it is still not commercialized, right? Despite having so many advantages, obvious question comes that why it is not commercialized. And in fact, if you see so I will come to, okay, let me tell about it. So what happens here as compared to the lithium ion battery, morning session and the lithium ion batteries, it's a intercalation mechanism, right? But here, more action. One side you have lithium as an anode, another side you have cathode, which is generally sulfur. Now, lithium ions go and react with sulfur, and it forms different kinds of compounds. If you see Li2S8, so you have sulfur, then you have Li2S8, it reacts with the lithium, then it forms Li2S6, Li2S4, Li2S2, and finally Li2S. So Li2S is the most stable compound, but it doesn't get formed directly. It forms through a series of products or intermediates, which are Li2S8, Li2S6, Li2S4, Li2S2, right? And then Li2S finally. Now this is called polysulfides, lithium polysulfides. Now these polysulfides, we can divide them higher order polysulfides, lower order polysulfides. Higher order means Li2S8, Li2S6, Li2S4. Lower order means Li2S2, Li2S. So these higher order polysulfides, which are but they are soluble in the electrolyte, right? So what happens once these are formed through surface? Since they are soluble in the electrolyte, they start going towards the anode. Okay, what happens? Lithium ions coming, it is forming the polysulfides. These polysulfides, they start traveling from cathode to anode. Okay, so this is called shuttling of polysulfides from cathode to anode. And because of that shuttling, there is a loss of material. The sulfur is getting towards the anode, right? So although the theoretical capacity of Li2 lithium sulfur battery is very high, we discussed 2600 as compared to 300 in the lithium ion, right? But because of this shuttling behavior, within very few cycles, the capacity decreases significantly, right? So this is one of the major problem of the lithium sulfur batteries, polysulfide shuttling. Of course, then we will see some other challenges. So this is a working mechanism. So S8, which is a octahedral shape, it works with the lithium. It reacts with the lithium. It forms finally Li2S. But if you see, it doesn't form Li2S directly. It forms Li2S8, 6, S4, S2, and S. And these higher order polysulfide, especially Li2S8, Li2S6, and Li2S4, they shuttle from cathode to anode. And then, of course, at the reaction with the lithium ion, it is simple. Lithium, it releases the lithium ions plus electron, and these lithium ions go to the cathode and they react with the sulfur. Now, the problems, the one problem is the shuttling, right? Because of that, there is a decrease in the capacity immediately after a couple of cycles. And because of this shuttling behavior, and material is lost. And second is sulfur itself. So, although we are saying that sulfur gives very high capacity, right? Very high energy density sulfur. But sulfur in itself is a insulating compound. Now for batteries, right, you need something conducting matrix so that you can conduct the electrons. But sulfur in itself is a very insulating compound. So that's another problem with the sulfur, although it is having high energy density. So what we do, we need some conducting matrix along with the sulfur, which can facilitate the electrons transport. So that is one. Third, this self-discharge and insulating nature and the volume change. Now, volume change means when this Li2S8, Li2S6 are getting formed, there is a change in volume. So when there is a change in volume and you have a packed cathode, then what will happen? Cathode, there will be cracks because of the volume change. So there will be a failure of your material and battery will be die down. So these are the practical challenges, although it is having very high energy density, theoretical. So in order to meet the energy demands, we need to overcome some of these challenges. How to suppress the polysulfide shuttling, how to address the volume change during the charge and discharge, how to address the insulating nature of the sulfur. So these are all possible problems on which we want to work on. And so one possible way is that on the cathode side, we use some heteroatom doped material, right? Or something which is conducting matrix. So the role of this heteroatom conducting matrix is multifold. One is conducting matrix, it facilitates electron transport. If it is heteroatom doping, through that heteroatom doping, we will try to chemically bond these polysulfides onto the cathode itself so that they do not shuttle, right? So we will chemically bond, link with the some heteroatoms, right? Maximum we can allow them to go till the separator, but they should not cross the separator, right? Sometimes we do the treatment at the separator itself, right? Or sometimes we put a physical barrier that is called interlayer, right? Although in the uh, industrial commercial scale it will not be very useful, because when you are putting a physical barrier interlayer to stop the shuttling behavior, you are basically adding extra weight, right? And that interlayer is not offering you any capacity. So you are adding certain material which are not adding any capacity but increasing the weight. So your energy density, which is with respect to weight, that will be reduced, right? But that is one possible way to have the interlayer where you physically suppress the polysulfides not to travel, right? So there are various ways. So now what we are going to do, we are trying to address these challenges by using the multifunctional carbon materials, right? So multifunctional carbon materials, basically high electronic conductivity, carbon is conducting, right? Many forms of carbon are conducting. So this conduct, when we make the carbon sulfur composite, then we can address the insulating nature of sulfur. So generally we prepare the, so it's not only the sulfur which is used as a cathode, we use sulfur carbon composite as a cathode, where carbon matrix facilitates the electronic transport, right? You can easily do the heteroatom doping in the carbon materials. You can dope nitrogen, you can dope sulfur, you can dope some other iron, nickel, cobalt, heteroatom doping. That is also possible with the carbon materials. And you make porous carbon, activated carbon, porous carbon. Once you have porous carbon structure in the cathode, what will happen? That porosity will allow you to address the volume change, right? So rather than having a solid matrix, you have a sponge-like porous matrix, where if there is a volume change, that volume change can be accommodated inside the pores, right? So by simply using the carbon materials in a different way, multifunctionality, we can address most of these challenges. Sometimes carbon is a non-polar compound and these polysulfides polar. So polar and non-polar interactions that helps in polysulfides to attach with the carbon, right? Sometimes if it is not happening, you do the some functionalization in the carbon. Carbon functionalization is very easy. Through this functionalization, you attach the polysulfides chemically, physically, whatever way, so that polysulfides do not travel from the cathode, right? Sometimes even we use the interlayer I was talking about, we use the carbon material as an interlayer, right? So that, but as I suggested, we will not go with the interlayer because it is not really good for the commercial application, but one can do for the lab scale thing. So what we are going to discuss, we have three materials we will discuss. One is agriculture waste, banana peduncle, right? We will convert this banana peduncle waste into a carbon, activated carbon, and we will use it as a carbon sulfur composite. Second is, I will show you. I will show you that what is, yes. Yeah. Second is synthesized carbon from the zero zen, right? We are working on this material for last 20 years. This is very organically synthesized material and very cheap way of synthesis. But we will do some kind of bimetallic integration into it. Third, we will use the same material, but we will dope it with the nitrogen and sulfur, so that this doping helps us further in polysulfide shuttling. And then I will show you that it's just not only at the lab scale, we will go the full cell. Then one of the example we will show you how it can be taken as a next level in terms of scaling up of the material for the commercial application. So we did the scaling up, and then also not just the coin cell, we have also attached the pouch cell fabrication. So as I was mentioning, so this is your banana peduncle on which, right? Yeah. Banana peels, you might mean banana stem, people have worked, but this is banana peduncle, which nobody has really looked into it. And second is zero gel, and third is the zero gel with the nitrogen sulfur doping. So let me go to the first example. So what we are doing, we are taking the banana peduncle, cleaning it, doing the regular activation. I'm not going into the detail, but regular activation, we can do the steam activation so that we can make more porous surface from the banana peduncle after pyrolysis. So what is this process is, when you take the banana peduncle, in fact, we have seen without outer layer, without layer, right? You can do in both ways. Dry it, then you do the pyrolysis at 900 degrees Celsius, 500 degrees Celsius, and then do the KOH activation. So you put into the acid KOH, sorry, alkali KOH, and then you activate the pores, which is very standard process of chemical activation, right? Very standard process. And then you get finally activated carbon derived from the banana peduncle, right? Now this activated carbon, I mean, we have regular done the testing. In the specificity of the time, I will avoid going into the details, but we've done the regular characterization, what kind of carbon it is, whether it is amorphous carbon, graphitic carbon, Sardian Raman. Then we have the BET surface area and the pore size distribution, right? So these are the regular statistics of any material which we use. We do that, and then we test it for the electrochemical performance. So now what we see, there are four cases: without activation and with activation, and with outer layer, without outer layer. And electrochemically, we can see that this is showing the two redox peaks and one oxidation peaks, which is converting into Li2SX, higher order polysulfides, lower order polysulfides. And finally, we see the discharge capacity, we see the cycle number. And what we see finally here is that even with this, let's say, uh, uh, we go with the 1C in charging, there is a continuous Coulombic efficiency which is being maintained at 1C nearly around 1000 milliampere per gram, which used to be around 200, 250 for the lithium ion batteries. And here we have taken the sulfur loading 1.6 milligrams per centimeter square. Take the electrode, the sulfur loading, you can get high. If loading is limited means you are in weight, maximum density. But in need to have loading. So 1.6 milligram per centimeter is reasonable. Ideally, we can go to 5 milligram per centimeter square also. And then we compare these with the available literature, different kinds of biomass. And you can see, you take any parameter in terms of BET surface area, in terms of initial capacity to final capacity, and then how much retention you have got and how many cycles. So we got up to 200 cycles with 61% retention, and 100 cycles 80% retention at different current density. And you can see the initial capacity and final capacity. These numbers are almost higher to any of the literature which is available so far, the lithium sulfur battery. One of the reason was the surface area is very high. You can see around 3000 meters square per gram surface area for the activated carbon from the banana peduncle, which is very high. So high surface area means high porosity that can accommodate this volume change. Conductivity, we have seen in the XRD and Raman, enough conducting, and that is facilitating the electronic transport, right? And this carbon, as I said, polar non-polar bonding that helps in polysulfide shuttling, suppressing that behavior. So that was one material. This is already I've discussed. Second, I have taken the RF0 gel carbon, which is very easy to synthesize. I will just mention it. We filed the patent also in this. Let me come to the process. So we take certain chemicals, organic chemicals, resource formaldehyde, very easily available, very cheap materials. Mix it with the K2CO3, which acts as a catalyst in the water. It's a solution. We prepare formaldehyde, K2CO3, and water. You just mix it, stir it for 15 minutes. You will get a clear solution. In that solution, we have added PBA, polyvinyl alcohol. Then we have added two salts, iron acetate and cobalt acetates. The purpose of iron and cobalt is to impregnate these carbon material with the iron and cobalt. Iron and cobalt, they help in increasing the conductivity further, right? These are metallic compounds, iron, cobalt. So once you embed iron and cobalt in the carbon matrix, you increase the conductivity, right? You need increased conductivity for the electronic transport. And what was the purpose of PVA? Polymer, right? Once polymer solution is added and then you heat it to convert it into carbon at 900 degrees Celsius, what will happen? At 900 degrees Celsius, this polymer will degrade. When polymer will degrade, it will increase the porosity of that carbon matrix, right? So you have a matrix in which some polymer molecules are there. And when you are burning it, when you are paralyzing it, polymer is degrading. So that polymer degradation is leading some kind of porosity, right? So the role of PBA here is as a sacrificial polymer. It is sacrificed to create a porosity. So we are increasing the porosity by adding the PBA. We are increasing the conductivity by adding the iron acetate, cobalt acetate. And this RF0 gel that itself is having very good yield of carbon. It gives you around 65 to 70% yield of carbon, right? So all these, what I'm telling, why I'm telling you all this, there is a rationale behind choosing any of the material with which we work. So we mix it, gelation, then it's a zero gel. Zero gel means room temperature, I mean, oven. If it is dried in the supercritical condition, it is called cryogel. If it is, if it is dried in supercritical condition, it is called aerogel. If it is dried in the freeze condition, it is called cryogel. If it is dried in the oven, it is zero gel, right? All these different gels, they give you a different porosity. But supercritical drying, freeze drying, they are very expensive. So rather than increasing the porosity by methods, simply what we have done, we have added PVA to give the porosity. So finally, what we get, iron cobalt doped RF derived carbon. And then you diffuse it to add the sulfur into it so that sulfur is induced. And finally, you have sulfur carbon composite. You take the sulfur carbon composite, add carbon black and PVDF as a binder, make a slurry, and then coat your electrode with that material. This is prepare electrode. Again, this is what physiochemical properties look like. RF0 gel particles like this. Again, I will avoid, but this is like typical XRD, Raman, same thing, and pore size distribution and surface area. You can see the TM picture, these black dots which are appearing. This is nothing but iron cobalt particles inside that carbon matrix, right? So here, if you see, as compared to the previous images, if you can see, there is a much stable performance. The decay is less, even at higher current rate, 2C, 4C. The C is just, I'm telling you, C is current rate, current density. Generally, for mobile devices, you use very low current. where the C rate is 0.1, 0.2 maximum. When you want to go for the electric vehicles, you need high charge rate, C rate. There it is around 5C. Okay, since if you are accelerating the, but 2 to 5C is a good high. We want to test our material mostly for the lithium electric vehicles. So basically for the high current rates, 1C, 2C, 4C, 5C, up to 10C. Like so, we have tested this material at 2C and 4C, and we can see that capacity is much more stable than the previous case also, right? And numbers are also on the higher side than the previous case. Again, sulfur loading was 2 milligram per centimeter square, which is more practical case, right? We can reduce it to 1. We can get more higher numbers, but that is not the purpose. Again, with this material, this kind of material, carbon, nickel, cobalt doped material, we see the uh, mm, uh, comparison with the literature, and we can see the sulfur loading. Even we have gone with the higher sulfur loading of 4.2 milligram per centimeter square, right? So this sulfur loading is very critical when you really want to develop it for the practical purpose. And again, you can see the capacity and cycle numbers. We went up to the 600 and 400 cycles, and even there we are able to retain more than 60% of the capacity. Now, third one, we have taken the same RFG material, but doped this time with the nitrogen and sulfur. Now, again, nitrogen is used to enhance the conductivity, right? And sulfur is anyway because we are using it for the lithium sulfur battery. So that was the reason. So sulfur introduce the sulfur carbon bonds that improves the polysulfide affinity. Because of the sulfur carbon bonds, it is easy to attract these polysulfides towards it. When it attracts easily, it means they will not go towards the anode. So you are suppressing the polysulfide shuttling. And similarly, this nitrogen doping, of course, it helps in the conductivity, but we have seen conductivity is increased by iron cobalt also. But nitrogen doping, it creates strong loose basic sites that chemically anchor the polysulfides. So they chemically attach the polysulfides towards it, which is again another reason they are using the nitrogen doping. And both when we use simultaneously nitrogen and sulfur, dual doping strengthens the chemical confinement, accelerates the kinetics, delivering the much better cyclic stability. So here we have, we have taken the same PBA solution, resorcinol formaldehyde, K2CO3, same thing, but added this time into the nitrogen and sulfur into it. So finally we get nitrogen sulfur derived RF carbon, which we did the ball milling so that we can get fine powder. And this ball milling was later ball milled powder was used for the battery testing. Again, similar, same characterization we have done. Of course, we can see, I mean, if we compare the previous Raman and data, we can see the, Raman ID by IG ratio is 2.54, which basically shows it is more graphitic, it is more conducting than the previous carbon. Again, the performance, and in fact, now if you see one remarkable difference in the performance, if you see here, the capacity, if you see the night 5 means 5% of nitrogen sulfur, 2, 5 and 10. 5, there is a little increase in the capacity first, then decrease. This little increase in the capacity, this is a signature for the nitrogen doping. So nitrogen doping, what it does, it activates the materials. So after initial cycles of charge and discharge, material is reactivated. Once it is reactivated, then you get more capacity. So that's why we have nitrogen doping, that there is a slight increase in the capacity after a few cycles. So again, here also we have done with the 3C current rate, the sulfur loading of 2 milligram per centimeter square, and we get very stable capacity as compared to the previous case. Here we went even up to 1000 charge and discharge. We went up to 600. Here we went up to 1000 cycles. This is again a literature comparison, and of course we see a more effective sulfur loading up to 3.8, and even with that we got the higher numbers in terms of capacity retention and cyclic efficiency. So these are the three materials which we have shown. One is the agriculture waste, by which bio-based we have used the carbon. Then there are two synthetic materials which we have taken. In one approach, we have used bimetallic compound iron and cobalt doping. Second, we have done the nitrogen and sulfur doping. And among the three, I think this nitrogen sulfur doping that worked best for us. So finally, what we have done, we want to now take it to the next scale. So this material out of the three, we have chosen that nitrogen sulfur doped carbon is working better. So now we want to scale up this material, right? So we have done the scaling up of this material at the larger scale. So first we started with the lab scale where we go. And then the next attempt we went up to 50 gram, and finally we went up to 280 gram where the solution overall solution was 1 kg. So this is how we have scaled up this material from 2 gram lab scale to the number 280 grams. And what we see here now, in the lab scale, the gelation was 85 degrees Celsius, 72 hours. When we were drying this material, we were drying this material at 85 degrees Celsius for 72 hours, 3 days. So what we have seen, if you want to really scale up for industrial purpose, you cannot have any process which is going for 3 days, right? So what we have done here, we have now increased the gelation, but we reduced the gelation time from 72 hours to 2 hours, right? So and then we have checked that are we compromising anything in terms of final properties. But luckily, rather than compromising, we got even improved performance when the temperature was increased and the gelation time was significantly reduced from 3 days to 2 hours. So that is much more industrial adaptable process than the previous cases lab scale. So same thing we have done now, this time iron cobalt, and then we have done melt diffusion, and gelation time now is increased from 85 to these are different conditions. Even we have changed the temperature also. Earlier it was 1100. We further we went up to 1000 degrees Celsius. And what we see, if you see the specific capacity, 1100 1 hour, it was getting 1315. And when we reduce it to 1000 2 hours, we are even getting little more than. Okay. So by reducing the temperature also from 1100 to 1000, that is much more beneficial for industrial purpose, right? And of course, the gelation conditions are very much changed. 110 2 hours, we even got little higher capacity, 1390, right? So with these new parameters, little bit tuning, we are able to retain the capacity, and in fact, we are able to get little higher capacity. So these were the final parameters which we have tuned for the scale up. And in terms of electrochemical properties also, we can see even at 1C, we are getting much stable capacity. Morphology of the scaled up material is also same as compared to the lab based material. This is how it looks like, the overall solution. So this was for 50 gram. For that, we have taken the initial solution of 525 ml, and finally we got this for that. And see, there is no change, hardly any change in the morphology, and physical properties, electrochemical properties more or less same. So what we want to convey is that when we want to scale up with little fine tuning of the parameters, we were able to retain or rather increase the electrochemical performance to the as compared to the lab-based material. So this is another example where we went up to 900 gram of composite, where 280 gram of carbon was scaled up, and finally we got 900 gram of composite in the this scale-up work has been done jointly with the ARCI, which is a institute in Hyderabad. Their mandate is for the scale-up, so we have done this work with them. Again, if you see, even 900 gram material morphology remains same, and this is structural and electrochemically also. Even with the 2C current rate, we are able to go 300 cycles with hardly any change in the cyclic stability. Now, next step, what we have done, we went for the pouch cell, right? So far, it was half cell. We went for the full cell. Even in the full cell, we went to the pouch cell fabrication. So, in the pouch cell fabrication, what we have done, here are the different steps. slurry preparation, aluminum foil pretreatment, then there is line coating of the electrode material, drying, calendaring, electrode cutting. These are the various steps in the pouch cell fabrication. We have done all these steps and finally made a pouch, right? Pouch cell battery of the lithium sulfur. So anode here was thin lithium foil pressed on the copper foil. Copper foil works as a current conductor, and and cobalt doped RF sulfur carbon composite with the sulfur. Separator was used polypropylene membrane and electrode to sulfur ratio 7 milligram ml per gram. So these are all some recommended parameters for the pouch cell. We went with, and then we have checked the property with the pouch cell with good discharge capacity with limited cycles. We also did the post cycling, how it is behaving after post cycling, and we maintained that structural integrity is maintained in these material even after continuous cycling of charge and discharge. So just would like to summarize that we have scaled material up to 900 gram, and this material was used for the pouch cell fabrication, and we operated this pouch cell with the sulfur loading 3 milligram per centimeter square. EYS ratio set for actual conditions which are used at the industrial scale. So we maintain those conditions and that this on a pouch cell level. So basically, this is just a summary that we have done the coin cell with different kinds of compounds: RF0 gel carbon, nitrogen sulfur doped, iron cobalt doped, or banana peduncle derived carbon. One particular material which was working best for us, and from that material we have done the scale up, and with that scale up material we fabricated the pouch cell and tested the pouch cell under the realistic conditions. Now let me briefly switch to the another battery chemistry which is called metal CO2. So this metal CO2 battery, which is a very new concept, almost 5 years now we are working in this area, and in India, we were the first group, and now I know at least there are 2 or 3 groups which are working in metal CO2 battery. But we were the first to start this work in India in metal CO2 battery. Now, this particular metal CO2 battery, you see there are 2 kinds of rotation. One is Earth, one another is Mars. So this is aimed for 2 atmosphere, Earth atmosphere and Martian atmosphere. I'll tell you the region. Yeah. So we all know about the Earth atmosphere. CO2 emissions are there, which are causing the greenhouse gas, climate change, whatnot. And this is concern for us, even when the CO2 concentration is how much? Around 400 ppm, right? Even that 400 ppm of CO2 emissions is a problem for us in terms of climate change, greenhouse gas, and all that. So there are a lot of efforts going on in the scientific community where this CO2 is being converted into chemicals, useful chemicals. A lot of research is going on. But the issue is that all this process where CO2 is getting converted into chemicals, they are very energy intensive process, right? So people are looking for developing various kinds of catalysts and all that so that they can reduce the energy input. But as of now, these are very energy intensive process. Here we are demonstrating the use of CO2 to convert into the electricity by the electrochemical route, direct conversion, right? That is one aspect. Second is we are developing this battery for the Martian atmosphere. You have seen interplanetary Mars missions, Mangalyaan and all that. When we send these missions, right, they also need some energy storage devices for landers, rovers, right? They are working there for a few months to few years. They need energy storage. So currently we are using the lithium ion batteries, which are very expensive, limited energy density. And when you add it with the payload, that increases the volume, that increases the mass, and of course the cost of these missions. So the idea is, what if we utilize the local atmosphere in the Mars? If you see the Martian atmosphere, it is 95.3% CO2, right? Here we are talking about 400 ppm. Martian atmosphere is 95.3% CO2. So can we utilize the local CO2 atmosphere on the Mars and use that CO2 to provide the energy as an energy carrier for the lithium CO2 batteries? And we can power these devices, landers, rovers, by having the lithium CO2 battery technologies. So this is the two aim on which we are working. One is the Earth atmosphere to address the CO2 emissions. At the same time, for the Martian atmosphere to propel the landers and rovers to increase the lifetime of these interplanetary Mars missions and minimizing the cost. So with this aim, we want to develop this metal CO2 battery. And if we compare this lithium CO2 metal CO2 battery with the existing lithium ion batteries also, in terms of capacity and all that, there also we have advantage. So if you see the theoretical capacity of lithium CO2 battery, it is 1876 watt hour per kg, which is almost 7 to 8 times higher than the lithium ion batteries. So apart from whatever reasons I told you to take care of the excess CO2 emissions and all that, even in terms of energy density, it is much better than the lithium ion batteries, right? So this is another way to look into the futuristic energy storage devices, where not only you are addressing the gas emissions effect, but also increasing the energy density of these power energy storage devices. Not only lithium CO2, if we go for the potassium CO2, sodium CO2, even then battery theoretical density is much higher than the lithium ion batteries, right? So timeline shows the first lithium-ion battery. I think Professor Martha might have talked in the morning. It was introduced in the market in 1991, right? In the by company Sony. And this lithium CO2 battery, which was conceptualized first time in 2014. And 2016, 2020, there was first report on potassium CO2 battery in 2020. So it's a very, very new chemistry on which we are working. If you see the timeline in terms of this lithium CO2 battery development, this is one paper from the literature. First lithium CO2 battery was introduced in 2013, scientific literature. But when was introduced first time in 2013, it was introduced as a primary battery. Means it can be used at the one time. Next year, there was a first report on secondary battery of lithium CO2 in 2014. And since then, there's a lot of research going on. And then you can see in 2016, sodium CO2 battery was reported. 2018-19, they introduced new materials. 2020, there was a potassium CO2 battery. And 2021, which is under the red box, LCB, lithium CO2 battery, suitable for Mars exploration. That was a report from our group, okay, Patak et al. So this was the first contribution in that direction from our group, in which we have demonstrated that this lithium CO2 battery can be used for the Mars atmosphere, right? And of course, since then we have also made a lot of progress in this area. So what happens here? Unlike the typical batteries, the difference between and that's also a technical challenge. So typical batteries, whatever it is, lithium ion, or lithium sulfur, sodium ion, whatever. You have an anode, cathode, electrolyte, separator, right? And it's a closed compact system, right? But here you are introducing the CO2, you are introducing the gas, so it cannot be a closed system. So one side you have to continuously push the CO2. So it's a semi-closed or semi-open system, unlike the other batteries, right? So here CO2 is being pumped from the one side. So that's why you can see cathode side, there is a hole, cathode can with the holes. Through that you can introduce the CO2. So it's a semi-open system. And it's an electrochemical reduction of CO2. And the overall reaction right now, what is happening? Lithium ions, they react with the CO2. It forms Li2CO3, metal carbonate plus carbon during the discharge. And charge, it's a reversible process, right? So it's a charge and discharge battery. So lithium ion or foil that acts as an anode, and or on your cathode there is CO2, right? And reaction happen at the cathode. And generally you use the LiTFSI as a electrolyte based molecule and then separator. And this is assembled in a particular chamber where you can continuously push the CO2. So there is a separate chamber we have created to test the lithium CO2 battery. So inside the chamber, there is a CO2 atmosphere. So this is what happens: metal anode, electrolyte, catalyst on the cathode side that you can accelerate the reaction, and porous cathode, unlike the typical case. So it's a porous cathode through which you introduce the CO2. So lithium ions comes, porous cathode side, CO2 comes, it reacted, it forms Li2CO3, and this is how you get. Now, what are the issues with this battery? Right, a lot of technical challenges. First and foremost, the lithium CO2, lithium and CO2 reacts, it forms lithium carbonate, Li2CO3. This Li2CO3 is a very, very thermodynamically stable compound. And that was the reason when it was introduced first time in 2013, it was introduced as a primary battery. That one time it reacts, forms the Li2CO3. That's it. Because this Li2CO3 decomposition is very, very difficult. Thermodynamically is a very stable compound, so it doesn't decompose automatically to get it as rechargeable batteries, right? So you need to bring down the activation energy of that reaction. For that, you need lot of catalysts, right? So that you can establish the reversibility of this process. That is one. Second, carbon is also getting formed, Li2CO3 plus carbon. This carbon is getting deposited on the cathode side. It blocks the active sites. So after few cycles, everywhere it is carbon deposited. It does not allow further CO2 to react with the lithium. So after few cycles, capacity comes down, right? So and then third is, even if you want to decompose this lithium CO2, lithium carbonate, you need more energy to decompose it. So rather than what energy you get from the battery, you have to put more energy to decompose it. So it's not energy plus process, it's energy negative process. And third, even if you put more energy in terms of more voltage, then the electrolyte will decompose, right? So you cannot go beyond a limit. So these are the real technical challenges which really limits the applicability of lithium CO2 battery in general. But of course, as a scientist, we need to address these challenges, right? So our group is working in that direction. So because of this, there is a lower practical energy density. As I mentioned, theoretical density is very high, but practically it is very low. Cycling capability is very low. After few cycles, carbon is deposited. You are not recycling. And high energy intake for charging. Charging, it takes more energy rather than what you get from the discharge. These are the practical challenges. Yes. So what our group is working, our group is working on multiple directions, right? We are using different kinds of catalysts, electrocatalysts, so that we can reduce the activation energy of the reversible process, charge process. So that this lithium carbonate, which is getting formed, Li2CO3, that decomposes much better, much easier than the current one. Then we are also working on cathode structure, so that it is more porous, more accommodative, so that this carbon which is getting deposited, that can be taken care, right? So that you can have more cycling. Third is electrolyte. Remember, we want to develop this battery for the Martian atmosphere. Martian atmosphere temperature and pressure conditions are very different what we have in the Earth, right? Temperature varies from -20 to +50, +60. So you need electrolyte which can take care of this temperature variation. So we need to optimize the electrolyte. Then the pressure. Here it's a 1 bar. There it is 1 millibar, 1000 times less, right? So you need to have material electrolyte which can withstand those pressures also. And of course, lithium, we are starting with the lithium CO2, but in future we want to go with the sodium CO2, potassium CO2. And finally, theoretical explanation, because this is very new chemistry. Few groups have worked, they have proposed some mechanism, but we are not sure about it, that it is really happening. Or especially under the high temperature, low pressure conditions, the temperature or the reaction path might be different. So we need to look for the reaction mechanism also for the better theoretical explanations of the phenomena which is occurring. So with this, I will just briefly tell few examples. So first, we have used the catalyst to improve the performance, and this is where we have used ruthenium nickel multi-volt CNT catalyst. Ruthenium nickel has been used in the literature to reduce this overpotential. So we combined the multi-volt CNTs because multi-volt CNTs offer you high surface area, more porosity. So we combined this ruthenium nickel with the multi-volt CNT used as a catalyst. This work was published last year, I think. Yeah, cancer scan. So I was just mentioning why ruthenium nickel, because ruthenium promotes easier formation and decomposition of this lithium CO2, lithium carbonate, and nickel has been used in the literature to increase the reversibility, and we used both so that we can combine the electrocatalytic activity, and MWCNT used as a support so that increase the electronic transport. I'm not going into the detail of synthesis, but it's a very hydrothermal process. You have taken the multi-volt CNTs, nickel salt, ruthenium salt, do the hydrothermal process. Finally, you get multi-volt CNTs with the ruthenium nickel catalyst. You can see the multi-volt CNTs with the dots, which are ruthenium nickel alloy. And then we did characterization with that and tested with the batteries. And what we can see, so we have used CO2 atmosphere, and also we have used Martian CO2 atmosphere. So Martian CO2 atmosphere, actually, if you see, it's a 95.3% CO2. Remaining CO, oxygen, nitrogen. So we have simulated the gas. We asked the vendor to supply as per this gas composition, which is actually in the Mars. Then we use the actual Martian atmosphere gas, right? And what we have seen, the actual Martian gas atmosphere, that works even better because there is a CO, carbon monoxide. The carbon monoxide, it helps in more density, more power, right? So that is even helping us rather than pure CO2. So what we can see is here that we are able to use atmosphere gas, and we are used to demonstrate its use for different. And cycle number also here we have around 30, but later we went beyond that. I think I will just go to that. Here we have used candle soot carbon rather than multi-volt CNTs. Again, I'm not going to the detail, but our group has really worked on this candle soot carbon in last 10 years. And this is used as a very effective carbon material rather than multi-volt CNTs. So here also we have demonstrated that candle soot carbon, it works better than the multi-volt CNTs, right? Why? Because if you use this candle soot carbon, it is actually having the carbon nanoparticles of 40-50 nanometer. And this is one of the most facile way to produce the carbon nanomaterials. You simply lit the candle, collect the soot, and when you see the soot, it is having carbon particles of 40-50 nanometer. So why to go with the very expensive multi-volt CNTs when you can get the same properties or even better properties with the candle soot carbon, nanocarbon. So we have replaced the multi-volt CNT with the candle soot catalyst, and this is I can skip that. And then we have seen, we have compared candle soot multi-volt CNT, did the same testing, and what we have shown here, yeah, for any current density, if we test it, the number of cycles for which we can recharge and charge this lithium CO2 battery is higher in candle soot as compared to multi-volt CNTs. For example, at 200, we went up to 68 number of cycles charge and discharge. But with the candle soot, we went up to 84 cycles, right? So at any current density, there is a more number of cycles, more number of better cyclic stability as in the carbon as compared to multi-volt CNTs. Similarly, in the capacity, we are having higher capacity with the candle soot carbon. So previous case, we have taken ruthenium nickel on the multi-volt CNT. So this time now what we have done, we have replaced that multi-volt CNT with the candle soot carbon. So we prepare the ruthenium nickel alloy and deposit it on the candle soot carbon and use it as a catalyst. Same process. We have used hydrothermal process to deposit this. You can see candle soot carbon nanoparticles, and we are well decorated with the ruthenium nickel alloys, right? Well dispersed. And then we tested, and here you can see we went beyond 100 cycles of charge and discharge. Last time it was 84 maximum. Now this time we went beyond 100 cycles of charge and discharge. And even full discharge we have done. We went full discharge up to 16, 17,000 milliampere per hour, which is very, very high. If you want to use it as a primary battery, for example. So I will just summarize. The way forward is we are looking for different kinds of electrolytes which can be used for different temperature range, right? Because our ultimate aim is from -20, -30 to +50, +60 degrees Celsius. So that is one. Low temperature and pressure. So some work right now we are doing already in the low temperature. Pressure we are yet to start actually. So this is just a way forward. Development of electrolyte. We are looking for semi-gel electrolytes also, gel electrolytes, polymer gel electrolytes. Maybe the combination of solvent A and solvent, and so that we can address the conductivity, flammability, volatility, all these issues can be sorted out. Rather than working with a single electrolyte, we can work with a multiple combination of solvents for that electrolyte. Here are some of the recent publications from our group in that area. Yeah, I would like to acknowledge the group, and I'm on time, Muslim, right? So yeah, any questions? I will be happy to take some questions. Thank you. How much is biomass material from? Yeah, it's a good question. So there are a lot of biomass people have used, right? So as I said, there should be a rationale to use any material. So when we look for biomass, we see what kind of metal particles we can get from those biomass, right? Sometimes we get some kind of embedded metal particles in some biomass, right? So that is one. Second is wider availability of that biomass, right? So these are some of the things. Of course, for the lab scale, you can use any kind of biomass. But in the long term, if you really want to go for the industrial scale, these are some of the considerations you need to take care. Yeah. Yeah, so as a guideline, you can start with 900 degrees Celsius, but there is always a scope for improving it by optimizing it 1000, 1100. But it comes from the experience. But basic guideline to start with is the 900 degrees Celsius. Yeah. From the DISCOM's perspective, in rural areas, there is no power supply is not congested and all that. So, which energy storage solutions direction we see like we should pursue so that. See, we are talking about the energy storage. What you are saying is energy generation, right? For example, solar cells, right? In the rural areas, you can have the solar cells set up. But see, why do we need energy storage? Because these renewable energy sources, whether primarily it's in the rural area, let's say solar cells. Now, solar cells can produce or generate the energy in the daytime, but you want to use it in the night, right? So there you need energy storage devices, and that is where batteries comes into the picture. So for those kind of application, I would still say that fine batteries based systems are still much better. See, these systems which we are looking is primarily for the electric vehicles, where your energy density requirement is much, right? So their lithium-ion battery is having a limitation. Otherwise, it's laptop, mobiles, small devices. I think lithium-ion battery is still working much better. So those small applications is still fine, but this mainly for the great application, the electric vehicles, their lithium-ion batteries is having a limitation. Carbon source from? No, see, that's what I said. You can make carbon from anything, right? You take any organic matter, burn it, pyrolysis it, you will get carbon, right? But the question here, when you look for a material for this kind of applications, one is the quantum, how much you can get if you suppose your material works out very well in terms of technology. Now industry wants to adopt it, right? So these are some of the parameters which you need to consider. What is the availability of that material? What is the supply chain, right? You may have best technology, but if supply chain is not working, it will not go further, right? So even despite having so much of biomass kind of waste, still one of the most widely used is the coconut husk or coconut shell. This is still used at the industrial scale for the activated carbon. So we need to have all these separate factors which are beyond the science and technical thing. Yeah. Any other thing?
Sir, in one of the slides you mentioned the current density of this number of cycles.
Yeah.
In general, what is like number of cycles that we can
Current density number of cycles? No, I don't think so.
one slide you kept current density is there, and the number of like where you have shown 700 cycles.
Okay. Yeah. No, that is just to show that we can operate that battery for the different current densities. Yeah.
In general, what is the cycle?
No, no. So see, the idea is different here. We want to test our material for different current densities. So we want to go, let's say, 0.1 C, 0.2 C, 0.3 C, 0.5 C, 1 C, 2 C, 5 C, like that. So there, if you want to go, we go for the limited cycles. It's more a demonstration that 10 cycles we have done at the lower current rate, then at higher current rate, then at higher current rate. That is to demonstrate the different current densities applicability. But if you want to check the long-term cyclability, there you do it at a fixed current density. Okay.
How do you find the current density?
No, so current density value, as I was mentioning, that it depends on your application, right? When you're looking for the electronic gadget device, you are focusing on the lower current density, which is 0.1, 0.2 C, like that. You want to go for the electric vehicle batteries, you are looking for more current density, is 2C, 5C, 10C, like that. Okay. So it depends on your final goal, right? Some materials, they work better at the lower current rate. Some materials work with the high current rate, right? But you need to test them. You can have some kind of hypothesis in you, but ultimately you need to test it, right? That this material, for example, candle soot carbon, I can mention especially candle soot carbon, when we tested it first time in 2016, unlike most of the carbon materials. So if you see the lithium ion battery which you are using, they all have the carbon, right? But these are all low current application. When you go for the lithium ion batteries for the electric vehicles, Tesla, they don't use carbon, right? They are using LTO, which is having much lower density. But in terms of high current, that is much better. Carbon doesn't work better there. So that's why, but unlike the general carbon materials, the candle soot carbon especially, when we test it, it works better for the high current. It doesn't work in the low current. So it depends on the individual material characteristics, right? And of course, your final requirement, what you are looking for. Yeah, there is no general answer for that. Okay, I think Arup is here for the next talk. Yeah. Thank you. No, no, I have my places here. Oh, yeah. Okay. Thank you. Yeah. But yeah, what happened very big. But they had alternative actually. They went on our lunch and then they asked it. I did appreciate. Final days I was like, so they have managed, but I told those for invested aid, so I should pay. Yeah, anyway, now I think since we have everybody just take 2 minutes. So I think to another opportunity that we still have 2 months left in this prepare program. So you can utilize this opportunity to visit for longer duration. For faculty, it is up to 2 weeks, and students can come to 2 months also. This is till June 30th.
like so say now you have 3 months summer break, and so you can do have opportunity for yourself and for your students. Yeah. Since now you have visited the campus, you have seen the facilities, so now you can even decide better. So we will be happy to host more and more. I think yeah, just to be able to contribute to what you have to encourage the culture on right was right. And it's funny is that we will try to extend it for maybe I mentioned yesterday, we got the email from NIH yesterday that we'll try to review meeting is next week, next month. So if possible, we'll ask them that with no cost extension, if they can allow from them. Yeah. So try to use that opportunity. Yeah. Thank you again. Yeah. Please, you know, finally, again, do a thing which work at the also on you. It's hard. Let's keep you on training on that. Okay. The next one is the companies have knowledge health council to develop. We may have a lot of funding of the services. Probably if we think that let's have some ideas. I just take it here. I should take it. Because you know, that's one of the work on it is good. But the thing about all the things we are here, the price taking it hard to match it. The good significantly. We have the and those we check the price of our food to be like so that you have to be news to particle and then figure out in that. So, can we particle for AI? Yes, we have two coordinators. But these are at least two. So, I want one from here to the teacher. Or okay, okay. Yeah, yeah, I'm sorry. Yeah, I am not sure. I just close the screen. So I just yesterday I forget. You take his behavior is you said you need to get function of energy. Even nothing comes already especially checking any function. Yeah, that's it. I did go staging. He has 15, 16 hours and out of that. 17 things, yeah, some really more. But she came up and when that same time. Check is. At what time we're going to stop? So, we need to remind that we did from the right, it closing. Yeah. Hey, well, so I'm Murup Mahata from Department of Chemistry. I work on computational modeling on energy conversion and energy storage aspect. So computational modeling, as you have seen since class today, that it can be of different approaches.
I deal with atomistic modeling. So I see the atoms, their chemical nature, their physical nature, how they are bonded, and what kind of fundamental chemical and physical properties are arising because of those atoms, and how those properties are associated with the performance matrix of energy storage system, say voltage capacity. That kind of structure property correlation, it's not stable. Maybe that kind of structure property correlation I try to establish. So in this lecture, that's what I'm going to show, that how powerful this atomistic computational modeling is, how one can align very perfectly with experimental trends, and explain uh, some observation which is sometimes difficult to get from experimental characterization, and eventually how one can utilize the computational screening, material screening also, so that experimentalists also can get better idea regarding their synthesis and characterization process. So that's the target of my talk here to show. So focusing on the battery application. So as we are seeing since last 3 days, that that's a typical schematic of battery. We have electrode in both side, and the migrating ion that migrate uh, between the electrode, and we have electrolyte in the between. That's a very typical schematic of battery. Now, what are the bottlenecks? Key bottlenecks, fundamental bottlenecks are associated with the battery materials. So if we divide the component, if we look into the component into different aspects, we have electrodes and electrolyte, very broad way. Now the electrodes are associated with, the bottlenecks which are associated with electrode is lower voltage, lower capacity, low ion migration resistance, higher ion migration resistance, and of course the cost of rare earth minerals. From electrolyte point of view, that we are facing with lower voltage stability, poor ion migration kinetics, and of course the volatile organic solvents. So these are the major, uh, in general, bottlenecks which are associated with the electrode component and the electrolyte component. Now, if we dig into deeper, we can see that the different properties that I was telling, this performance matrix, they are associated with the different mechanism, the way their electrochemical storage mechanism behaves. As you can see that we have this one slide. You don't have here. We have pointer here. Okay, I can continue. Yeah. So you see that the different kind of electrodes can gives you the performance in an entirely different range. So if we go ahead with the intercalation types of electrodes, there, and if we compare with the conversion types of electrodes, their performance are hugely different. Yeah. Yeah. So we can see that their properties significantly differs by their types of electrons. That means what? They differ by how the working mechanism. So the difference between conversion type and intercalation is type, that how they behave, how the energy storage mechanism is operating there. In one case, only the migrating ion intercalate. It is a kind of layered materials. In another case, the entire cathode or anode, they convert to something else. So this is the fundamental difference in the two types. And the important point is here how different they behave. Now, if you go further, if you just within a similar type, if you do some elemental some compositional change, if you change their stoichiometry, you can have such even such kind of significant variations. So the point of showing here is that the properties of the electrode, they are fundamentally rooted to their atomistic properties. So we are going to see their atoms, how their stoichiometry, how their composition. So the chemistry is their composition itself. That means chemistry is there in their atomic properties itself. It will be more clear if we further dig into. So, so this one, that's called that this is the how the redox level is situated. If you see the fundamentally that the gap between the anode redox energy and the cathode redox energy, that gives you the fundamental voltage of the any battery. We are seeing this last few days. Now, if you compare the sulfur versus oxygen, sulfur contains 3p orbital, so it is higher in energy. So essentially, sulfur, if any electrode which has sulfur, that cannot stabilize the transition metal of like cobalt, nickel, or manganese, because it is staying higher in energy, and eventually this gap between the anode and cathode, that gives you the voltage that comes around 2.5 volt, much lower in sulfur cathode. Compared to if we see the oxygen has 2p, low quantum number, so the energy is much lower in energy. So now if you see the difference, it can now stabilize the transition metal, and of course that is why the lithium cobalt oxide is so popular as a electrode. And essentially we can get a difference of around 4 volt. So the voltage. So my point is that all these fundamental characteristic is arising from such atomistic properties. Now, if we look into the electrolyte also, electrolyte stability again depend on their where is this HOMO or LUMO. This is called the highest occupied molecular orbital. That means we have those orbitals in atoms 1s, 2s, 2p, 3s. Where you have the last electron, how far you have the electron. Some very 12 standard chemistry, if we try to recall. So depending on these positions, the stability of the electrolyte will depends. How? So electrolyte should be electronically insulating. There should not be any electron transfer along the electrolyte. Now we have three component roughly: anode, electrolyte, and cathode. So I have electron up to this level, HOMO in electrolyte. Now, if cathode energy stays, lie below this level, this electron can come to here, and that will do some unwanted chemical reaction at the interface, and which is detrimental, which you don't want. So we should choose a cathode which energy should be above from this HOMO energy level. Very similar way, if you look into the anode side, anode interface, anode electrolyte interface, we have LUMO here. That means if any electron comes from outside, from electrode, it should be here. Now, if anode stays here, above than the LUMO energy level, the electron will come from anode to the electrolyte, and which again we don't want. That will create some unwanted reaction, and which can form the solid electrolyte interface, ACI, that classic ACI what we can say. Now, of course, ACI can be beneficial, can be detrimental, but from fundamental aspect, that the my point of saying here that such energy level of in anode, electrolyte, and cathode, they determines their stability, their voltage, their stability. And where from all these energy levels are coming? They are coming from their very fundamental atomistic properties. Very fundamental atomistic properties like this, where the electron is 1s, 2s, 2p, 3p. That's decide the energy level, where they are. So if we have such fundamental knowledge from textbook, one can primarily design the battery components and their stacking nature. That's my point of saying here. So essentially, such kind of fundamental chemistry can give you such voltage window. These are the for the conventional material. So now this kind of problems is arising from the fundamental chemistry properties. What happens in the real scenario? There are many others actually. Some interfacial side reaction. If we have a liquid electrolyte, some interfacial reactions happens at the interface of electrolyte and electrode. Even if we replace the liquid electrolyte with solid electrolyte, then also the interfacial mechanical contact, their reaction, dendrite growth, this kind of scenario can appear. Focusing on the ion migration, as you know that the ion migration nature of the migrating ion is very important, because that's only decide the electrochemical behavior. So how they are solvated, that decides that how fast or how slow they are migrating in case of liquid medium. So all this, my point is that all these kind of issues which we are addressing, they are again fundamentally atomistic. They are originating from the atomic scale structure, bonding, diffusion pathway, and the electronic state. So whatever the performance metrics, voltage, capacity we are listening, they all are fundamentally rooted to this kind of very atomistic properties like electronic state, their bonding nature, their structures. So if we can look into such fundamental things computationally, we can reach to the real performance metrics. So that's my target. That's I'm going to show you now that how computationally we deal this kind of problem and how they are correlated with the performance, battery performance. So yeah, now if we see a close vis-a-vis comparison between experiment and theory, essentially experiment is robust. That gives you the direct validations. So that is important. That's the method. In computationally, okay, we can say something, but at the end we cannot show you the material. You have to do the experiment. So experiment is lasting, no question on that. However, there are some limitation in experiment where computational can really play important role. So if we just broadly categorize the three aspects from material synthetic point of view, from their characterization point of view, and their electrochemical testing point of view, we can see that, yeah, from material synthesis point of view, some materials are really costly. So of course we can essentially cut down the cost from, but major advantage of computational is in this aspect, structural characterization, particularly in the interface. As I told, in electrolyte electrode interface or any interface, if they are deeply buried, many surface characterization techniques are unable to locate them. That is one of the major limitation in experiment. So surface characterization technique cannot locate those deeply buried interface, what is happening there. So that is one aspect where computational can significantly contribute. And of course, there are several others, that the limited sensitivity towards light element like lithium, hydrogen, the limitation in the in situ methods or operando methods, and of course, the time scale. Experimental techniques has some limitation in probing some small time scale things. So they are also the computational technique, computational calculations can provide important insight. So to summarize, yes, we need to bring out the best outcome. We need both. We need both experiment and theory if we want to say in a very robust way. So in the coming slides, we'll see that how computational and experimental technique can complement each other. So now coming to the computational techniques, yes, there are several techniques even in atomistic modeling. Now we have these two systems that two opposite this accuracy and the largeness, they run in opposite directions. If we want to have accurate number, we cannot deal with large system. So to give a brief idea, one is very popular computational technique is DFT. Some of you might have heard, density functional theory. So is it give you the ground state property perfectly, very nice. If you can treat it in a accurate way, it can give you the very accurate ground state properties. If you have ground state properties, then of course you can predict the voltage, their stability, their diffusion very accurate way. But the problem is that it cannot include the temperature effect, and the major limitation is their size. It cannot handle more than a few hundred atoms. So if we have to deal with some dope system or something where we need a large supercell to so let's say for small doping, we need a large system. There, if it goes beyond few hundreds, we cannot use a state-of-the-art DFT technique. We have ab initio molecular dynamics techniques, yes, that can take into the entropy effect and the time scale. But we can handle more number of atoms also, but they are not so accurate like density functional theory, static density functional theory calculation. Of course, in classical MD, we can handle few more atoms, few thousand more atoms, but with the compromise of the accuracy of the calculation. Of course, machine learning again It can handle a large set of database, but with the compromise with the quality of the number. So all has some pros and cons. So depending on our what we are looking for, what kind of things we are going to understand, one can utilize the different atomistic tool. So how we typically do? Since beginning, I am talking about the atomistic. How we really do in simulation. Let's understand that. So let's take the classic example of graphite. So graphite, we know it's a layered material, and stacking is AB. That means the similar kind of layer is in the alternating layer. We have the similar kind of configuration, atomistic configuration, and the interlayer gap is around 3.3 angstrom. So this is an infinite layer, right? In the X, Y, Z three direction, they are infinite in nature. So of course we cannot take. So let's say if you have a 2 nanometer graphite sheet, we cannot take a 2 nanometer graphite sheet. We don't need also. We need the unit cell. If you recall in our very fundamental solid state physics or solid state chemistry, we we learned about crystal system. We had tetragonal, orthorhombic, monoclinic, cubic, so on, hexagonal, all these things. So there we learned the unit cell. So we need the smallest repeating unit. If we find the smallest repeating unit, that's all. That's all we need. We just keep on repeating it. It will give you the same property. So taking graphite as example, graphite there. So in the this is the unit cell of the graphite. So I have only one layer and the second layer. This third layer is repeating. You see this atom and this atom, they are exactly similar. So in order to describe graphite, I need this two layer, and in each layer I have to I need only. So this kind of this box, basically you can see the hexagonal box. Graphite is hexagonal lattice, where the A and B, basically this direction and this direction, they are equal, and C is different, and the angle between A and B is 120 degree, and between B and C is 90 degree. This is a typical hexagonal lattice of graphite. So if I want to simulate graphite, I will only consider these atoms which are inside this unit cell. So from structural point of view, I only need those few atoms to model. And then I will define this box, this hexagonal box. I will define these atoms. Their atom means their coordinates, how they are located. So let's say if this is the origin 0, 0, 1, if this is the x direction, it will have, let's say, 0.500. And if we project the vector, we will have some components, some fractional components here, and so on. So those atoms, those coordinate we need, x, y, z coordinate for those atoms, and then we will simulate it using the density functional method. I'm going to show what is density functional theory in a very general and brief way. So this is how one can simulate the atoms, simulate the materials. Let's say this is from the structural point of view. Now I'll go in a very general way. Maybe you will not go into detail. That how since beginning I'm talking about DFT, density functional theory. How that really works. Why we need that. Why that method is so popular in describing the atomistic properties. So we know Schrodinger equations. So we H psi equals to E psi. So it's basically the eigenfunction, and energy is the eigenvalue of the Hamiltonian operator. So let's see in a very brief way. So this is one classic example of quantum mechanics, particularly in one-dimensional box, typical linear uh, conjugated molecule one can consider. So my point of showing here to giving this, though this is not associated with the battery things, but I'm bringing the context that how we utilize the DFT and why DFT is so strong, so robust tool. So basically, one can have the if we know the wave function of this kind of model, this kind of systems. So wave function means it describe how they behave, how the functions are behaving. And then if we know the Hamiltonian, we can get their energy. So a function describes that depending on the different quantum number, how their distribution is, and how their corresponding energy is. So this is for particle in one-dimensional box. A classic quantum example. We can do this for hydrogen atom also, where we have only one electron. Hydrogen atom means we have only one electron. very similar way, we can solve the Schrodinger equation H psi equals to E psi. If we know the Hamiltonian, if we know the wave function, we can have the energy. This is for one electron. So what happens if it go to the two electron? Okay, so in one electron, primarily you have the interaction between the nuclei and the electron. If we go to the two electron, let's not too much focus on the equation. Let's try to understand in a very general way, since our background is too much interdisciplinary. So we have two electron here in the nuclei. Now just adding only one electron, how many interaction are appearing? We have the interaction between the two electron. We have the interaction in repulsion. We have there for each electron nuclei interaction is there. So eventually, uh, just adding one more electron, lot of variables are appearing. So typically, this is the Hamiltonian for the two electron system, where we have the kinetic energy operator and the function and the component for the electron nucleus interaction and electron electron interaction. Let's not understand too much in detail. My point is, now if we have more number of electron, the scenario is becoming so much complicated. Now, why I am bothering about these two electron and many electron? If we go to the this kind of system, very basic things, carbon, we have 6 electrons. So how complicated it will be to get the Hamiltonian and to solve the Schrodinger equation. Just if we have 6 electron, it is not possible in pen and paper. No way. Now forget about lithium cobalt oxide, graphite. So no way. So we cannot do it in pen paper. We need some method where we can solve the Schrodinger equation for many body problem, for many electron problem. So that is where basically this DFT, the DFT come into picture. There are many approximation methods are there. Again, I'm not going in detail. So the final target is to solve the Schrodinger equation for my material. I have graphite, I have few carbon atoms. I want to solve. So let's say I have 10 carbon atoms in my system. It will be 60 electrons. I have to solve my Schrodinger equation for 60 electrons. And that is too much complicated considering all those interactions, so on and so forth. So that's where the idea of DFT comes. What it does, it it approximate the let's try to read this. It's basically it approximate the electron as a electron density. All these interactions, whatever I told, different kind of interaction, they approximated as a electron density. It creates a one electron problem, one body problem. And eventually that is why we can treat it in a very easy way. Just if we know the coordinate of each atoms, I have 10 carbon. If I know their coordinate 000, 050, 500, then we can just make a density, we can consider as a density and problem and solve the Schrodinger equation. And then we have to solve the Schrodinger equation. We need the E, energy. So that is the idea of DFT and how it does in program. You might have heard few program name, the VASP, quantum espresso, CP2K, Gaussian, so on and so forth. This kind of course where basically this density functional theory is implemented, how they work. So we first make a initial charge density. I was talking about the density. We give a initial charge density. How that we do? That we do from chemical intuition. At what kind of interaction can be just from our textbook knowledge. And based on that, we give some density. And then we solve the Schrodinger equation. We get some wave function. We see that our input and output is very aligned or too much difference. If it's too much difference, we again use that and we work in this kind of loop. And eventually, when the density, our input density and output density becomes same, we stop our calculation. So yeah, this kind of loop we do. We give some density, we solve the Schrodinger equation, we get the orbitals, and so on and so forth. This is how, in a very general, rough way, how DFT works. So my point of showing is that since I'm telling that this atomistic modeling, so first I showed that how we took the atoms, then I showed how we treat the atoms. We treat the atoms means we treat the electrons. We treat their electrons. Everything, whatever we are getting because of those electrons. We are treating those electrons using this tool, this DFT tool density functional theory. Yes, please.
Conditionally including the repulsion of electrons and then calculating the energy.
Yeah, that's actually huge. So I tried to show So this is the final equation. Now we know the let's try to understand the if you have two electrons. So here we are considering the electron nucleus interaction. Here we are considering the electron interaction. This is how if we have two electrons. Now you just consider the summation how much it will be if you have six electrons. So that is the role of DFT here. Instead of so let's say roughly we know the coordinates and we have their corresponding electron cloud. That all that electron cloud we consider as a single atom, a single density, and then we do some approximation, some quantum mechanics approximation like variation, perturbation, and so on. So eventually, in a nutshell, we treat as a one body problem. If I have many electrons, it is only one single wave function we can have, one single orbital we will have. Now orbital can be located here and there, but it is a single orbital that we treat. That's how I want to mean this. I was telling now this charge density. This charge density, what I am saying here, it's basically the this wave function. What I am saying here, that is the wave function is orbital. We maybe if some of our chemists are more familiar with orbitals, physicists are more familiar with wave function. But the same thing is basically how how their how their bands are distributed and their energy levels are. So yeah, in this way we deal now. This is a very popular software VAS. We just give the I was talking about. No? So these are the coordinates. These are where how the atoms are located, and then how we are approximating the DFT. These are the typical input output file, and then we put it in the supercomputer. This is how it works. Now let's move to the technical things. So far I have showed that. Yes, all these materials properties are arising from very fundamental atomistic behavior, and then we showed that how we treat those atomistic behavior, how we make the model, how we treat them through DFT. Now see the result. Let's see. Since beginning, I am telling that it complements very nicely to the experiment. Let's see how really it complements. So I take the classic example of graphite. Oh, I have 8 minutes. So let's take the classic example of graphite. So graphite is popular. Graphite. The beauty of graphite as a ion intercalation because we have these pz orbitals, so it can interact with the interacting ion, and eventually that is why so ion migration is so popular in if you consider as anode. So what we do, we place the atom. Let's say we are going to see the lithium ion migration along the graphite. So this is our graphite, right? We place one lithium atom. It can be something else also if we consider some other intercalating ion pf6, and then we make that charge density and we optimize it, and from here, yeah, let's not we can calculate the migration barrier also. How we calculate the migration barrier? Let's say lithium stays in the honeycomb. Typical they call it honeycomb structure, graphite structures. So most stable where the lithium, which site is the most stable for lithium, that is this honeycomb structure. Now when lithium will migrate, it will migrate to the next honeycomb structure. Then so it can migrate to the other possible sites also. Then we we stabilize there, and then we calculate their migration barrier and so on. So this is how we model, and one can utilize the benefit. So as you can see from the movie, uh, that when the lithium moving from one honeycomb position to another honeycomb position, how much energy we need to have this. We can calculate this using computational model. So let's go a little fast in this way. One can calculate the barrier. Yeah. Now let's see. Let's take only one example and then we'll stop. Uh, so this kind of materials, graphite-like materials, they show some classic this kind of their charging discharge profile show this classic staging type. We call it staging type. That they are charging and discharging profile, they have very such stage kind of behavior. This is experimental plot. So where from this nomenclature come? If the lithium intercalate in every layer, we call it stage one. That means in every stage we have. If it only in every alternate two layer, we call it as stage two. If it is in every alternate three, we call it as three. If it is every alternate four, we call it as four. So this is the typical voltage profile of graphite like uh, graphite like electrode. So in aluminum battery, it has been found that they follow a typical stage 4 mechanism, stage 4 stage. So let's see how one can how computationally one can exactly reproduce this. So we started looking into the problem by seeing the so in this case our migrating ion is not lithium, it is aluminum chloride, AlCl4. First we see that now AlCl4 it can uh, it can stay in a tetrahedral or in a planar also. That first we check that within the graphite which is the most stable. Once we finalize this one, so in our case we found that it wants to stay within the graphite layer as a tetrahedral. Then next things in lithium we know that is the honeycomb position is the most stable position. But here if we want to do something from scratch, we have to find it out that at which site they will be most stable, and then we calculate that energy E, what I told, H psi equals to E psi. That energy we are calculating. Once you know which site, and then we try to see now many things we look into that how we proceed computationally. Now we have graphite in such. Now let's say one LCl4 is here. What will happen to the next LCl4? It can go in the next in the similar layer, or it can go to the another layer. How that will be decided? It will be decided by these two factors. One is that if it want to get intercalated in the same layer, it has to face this kind of repulsion between the ion. If it want to get into the another layer, then this layer has to open up. So which cost less, that process will be favorable. So in this way, once we know which is favorable, we can keep on increasing the LCL4 capacity, LCL4 loading, and eventually we can increase the capacity. And interestingly, we found here that that uh, the stage 4, as you can see here, as I was telling that this alternate 4 layer, it is most stable. We found that this is the most stable. So it's nicely complementing um, with the with the experiment. So I have many other things, but I have to stop now. And that's so just now only one example I showed that how computational even we can see the voltage also, we can calculate the voltage also. How in the morning you Dr. Norando was showing that how where from these kind of equation are originating. So if we know this, we can set the equilibrium. Once we set the equilibrium, we can calculate the voltage, and the staging profile exactly look like the experiment. So I'll stop here just with one example. I had many others to show on different aspect that maybe I can show one thing. It's called photo rechargeable. Since the last talk, there was a discussion on these energy conversion and energy storage. One idea is that becoming popular is the photo redox battery. So it is yeah. So photo rechargeable battery. So just to give a brief view, we can integrate the solar conversion and the solar light conversion, solar conversion and the energy storage systems together. So we can have the benefit from both sides. So in different kind of battery we can use it in lithium oxygen also, lithium sulfur also, zinc air also. We can make them the so basically one of the electrode will be the light absorber that will absorb the light and eventually store the light in the same device. So we are working on perovskite based photo rechargeable battery. This is one is very popular material as a light absorber. You might have heard this perovskite solar cell these days. So they use the perovskite material as a electrode that absorb the light, transfer the make the hole an electron, and eventually that electron we utilize in the storage process, and the lithium also migrate. So yeah, in photo rechargeable battery we can integrate really this energy conversion and storage aspect. So with limitation of time, I stop here, and but please feel free to have ask any question if you have some queries or anything. Yes.
The video showed the lithium moving from one honeycomb structure to the other honeycomb structure.
Yes.
So how come we have to, when they were calculating energy? So we have to move it till the energy gets stabilized or if it gets
No. So that is, so first we have to find out that where it is most stable. It is in the honeycomb structure. Now, if I want to see that how much energy I need from moving from one honeycomb to another honeycomb, so that is a things called NEB, large elastic band method. So that calculates that. So basically, it creates an image. Okay. So you have the reactant, let's say starting point, your ending point. Then when it will go, it will calculate the energy for each point along the path, and in that way, it will give you a saddle point like this kind of barrier, and that energy is called the migration barrier. So that much energy you need if the lithium wants to move through the graphite. That's how we calculate it. So we don't deal here the time. So migration barrier, I mean, how much time it is taking, that's another aspect. It is the how much energy you need to cross that barrier.
so there are some variables that you are given with space.
Hmm. Yeah.
So what those variables?
So those are just different file. We in one part in Postcar we give the atom coordinate where the atoms are located, just to define the system. If I want to model graphite, lithium cobalt oxide, I have to show that you know the crystal file, zip file, you know, right? Crystal file. So that is basically the information what you are getting from the crystal file. That is in the post. Now in the podcar, we are assigning that. So those are coordinate, right? In the zip file, it is the coordinate. Only the some numbers or my calculation or my software will not know that what is this number. So we have to define that at what position which atom is, and that we define through podcar. That is called pseudo potential file. That contains all the information which can create those orbitals or wave function. Let's say something like that. And we have another file we call it incar and k point. So all the incar k point podcar, they are designed that how I am going to get the energy, I am going to optimize the system, those some computational technique. And in, so once I have the correct information on those fine, then only my density functional theory simulation will work in a proper way, and eventually I can get the right structure and right energy. Yeah. There are many softwares actually. Some are open source. Open source means free to download and free to use, like Quantum Espresso, CP2K. Some are paid, like Fast. So there are many such softwares which where this density functional theory is implemented. Gaussian also is a software, but Gaussian can also handle this kind of material problem, but it is not so good because the basis set they use, the basis set means again in a general way how 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 we are describing our system. That's called basis set, and all these pseudo potential things. That is not so accurate in describing a periodic structure. Materials means it's a periodic structure, right? You have three-dimensional nature in all three directions. So Gaussian is good for molecular system where it is finite, some metal complex, that kind of things. In Gaussian also essentially you can simulate, but it is not. It cannot give you a accurate number of this. So depending on that, depending on your purpose, we can use the different kind of softwares.
But for graph structure
Mm.
in Gaussian, how to choose cases? It's
Yeah.
like but transition metal complex.
Yes. So it's basically, let's give you in a very general idea. If I go to in details, then I need some slide to show you the numbers, the equation. So let's put it like, what is wave function? If you we know p orbital, d orbital, s, p, d, all these things we know, right? If you remember, may I know your background? You are a engineer or a basic scientist? May I know your background?
My
Huh?
my MSc.
MSc background. Okay. MSc, excellent. Then you can follow me. So let's say if you recall the in quantum course we had the if we want to describe the dxy dxz we had some equation you recall. So that equation that we had some function there, right? Square, cube, some linear function, some quadratic function over there. That defines that how now if you do some change, let's say instead of this d square, some square, if you use cube, you will not get the orbital shape of d orbital shape. It will be different. So that's how basically you have to choose your basis set. That how accurately you want to describe the your atoms, basically your electrons. For metal, you will have some you may have some d electron. So d electron shape is different compared to s and p. Now the way you are going to define a s orbital, which is spherical, will not be similar in case of p, which is rambent nature. Correct? So that's the role of basis set. How accurately you are describing your orbitals, your functions. So based on that, we have to choose our basis set. Yeah. Yeah. Hmm. Okay. Oh, okay. Thank you. Thank you. Achha, okay. In the background. Nice. Thank you. Okay. Thank
Thank you. So with this, we have come to um, the WhatsApp that we close with WhatsApp and WhatsApp for energy. And if you remember what I told in the beginning, so the last events that was image energy, then you have clean energy yesterday. Today you have electrochemical energy. So storage systems. I hope see all these areas are completely interconnected. So it doesn't matter whether you are a mechanical engineer, chemist, physicist, material science, or chemical engineering, or right? So you have seen the complex model work done by the mechanical engineering. So, as we discussed, before at the end of Professor Chandra's talk, you see, this program is extended till now. Currently, it is July, and possibly it will be extended. So, I request in those who are interested to come and spend some time at IIT Hyderabad, please do write to NRF para. Please copy to the concerned faculty, and it is a nice way to come learn here. You had some glance already, with the area you wanted to explore, and you can come here learn, and you can send also your student where you can send. You have 2 months. You can send if you even a student is doing coursework, you can send in May. And if you are occupied with a lot of exams and all things, I request that you plan in May, June. You will be inside the. I told you you will be inside the building in the summer is not going to affect if you're coming early and leaving late, right? And you will be within the campus premises. And so I request kindly even inform your colleagues and the students and explore this research collaboration, which will improve. The this is the goal of NRFR, to improve the research in the spoke institutes, plus collaboration will extend, and also like I think joint proposals and other things in the future. So with this keywords, I thank you again, for all of you coming over here, spending 3 days, 4 days of your time, precious time. So without wasting much time, I'll conclude here and we'll distribute the certificates. That Narendra, you would like to say something? And so thank you all. Or you should. Yeah, I have shared my cards, or you can see the email IDs of the faculty, or you can ask Aslam. He will share with you the email ID and phone number of the concerned faculty. Do not hesitate to contact us. This is a good opportunity for you to explore. Okay. This thank you again, and I wish you all success and a safe return uh, from my Hyderabad. Thank you. And this see the names and so we'll take a group photo at the end. So we have the certificates. So I'll just read out the names. You can come over here. Maybe that Narendra I'll read out and them. Tina Sinkar. Next would be Radeshwari. Harsh Kumar. Yes. See, and just even equal what you got in the people, from some concept, I would like love to support these students, because they can carry out the research work. And they should be succeed in quality research to supply university. They have wonderful facilities. We should give it. I was really surprised, amazed of the facilities even IIT may not have. Yes, you should see. What I'm telling, you will see that you should visit that petrol facility on battery and related aspects. So the professor I convert department who does the yeah, professor Maniskan there. So I he has got big project of 10 crore or something. They have gone and so they are trying to establish a big facility. Thank you. Market Aman, next. Aman Punjab. Shankaraya. Ipsita. Marante. You are my Oh, Rahul Patel. Tina Shankar. Vikas Patel. Kushi. Okay, so far. You take Kushi, you take all the mission. Hyderabad Thinker. Wait 20. Srinivasan. Rameshwar Reddy. You have some more slides or something like yes, sir, it is heavy. Yes, sir. 8% only. Luggage Kumar. Kalyan Kumar. Maida Kalyan Kumar. Yeah, yes. Look, it's not great.
Thank you, sir. Thank you very much. Thank you very much, Dr. Narendra, Dr. Arup, and Mr. Stavraj for today's debate. And I thank all the speakers again for their valuable time. Let's meet at 2:40. Yeah, go. Snacks. The snacks ready. So please collect your snacks and then continue. So, if you feel this, you know what we promise.
Thank you,
Yes.
sir.
Thank you. So, no, so thank you. It will be very important. I do understand the pain and I am that's the point for example. Some of you can turn your phone again. That's not in I can come. They can see that for us. So, I can get this again. What's your report? You can just go. Okay. Thanks, man. Outside. Okay. Let's get you know that we're ready. So, thank you. So,